definitely. Then, and you shouldn't need a lot of tech, you don't need a lot of technical expertise in order to create one of these. You just need to understand their science. Don't advance my slide.
On it.
Okay, and here is where we connect your science, start connecting your science to the observatory, and it's through that classic tool, the exposure time calculator. And again, these are provided by the project, and I will, they model candidate instruments and observing modes and just tell you how hard it is, because the price tag on an observation is always basically the exposure time. Okay, and next, please. And then we have the critical science engineering interface, which is where the exposure time calculators connect to the real engineering models. And actually the science engineering interface is actually like, it's actually Brianne. So Brianne Starkey, everyone. Yeah. So, okay. So these are the 3 exposure time calculators we have available right now. So we have optical near-infrared imaging camera, ultraviolet spectrograph ETC, and a new chronographic imaging and spectroscopy exposure time calculator. I want to highlight this one. It's called PI-EDITH. It was developed by Eleanor Alai and Miles Curry, who are probably here somewhere. They're waving their arms over there. Yes. And I want to say I'm really pleased about this because this is a big upgrade over what we had during the LUVOIR and HAVEX days. They are available as web interfaces for the casual user through the Space Telescope website here that they're hosting. Point of contact for that is Jason Tomlinson. And soon these will also be available on GitHub, so you can run them locally if you want to do large numbers of calculations, or if you're a super user and want to tweak some of the things that are under the hood. Okay, so onward. So right, put your science into DISRA. We want more science case modules. We are working right now to turn some of the science cases we have already received from the HW working groups into modules, but that's not the end of the story. And there we go. Whoops. Okay, and again, we want people to get involved. There's, in addition to the science and instrument community science and instrument team that you've already heard about. Again, I want to highlight that the NASA program analysis groups are starting up a HWO science interest group, and this is another way that people can get involved at like any kind of level of effort, really. And finally, this is not the end. Okay, DISRA is the beginning of our science simulation work. It's broad, but it's low fidelity. It shouldn't be, none of these modules should be terribly computationally intensive. It's sort of 1D. But some science cases, next please. Yes, sometimes. Some cases will need more fidelity in order to be certain that we've accurately assessed the science return. So there will be, in the not too distant future, starting medium fidelity simulations that start to take into account some of the dynamic behavior of the observatory. Finally, for the very key, hardest 1 or 2 driving science cases, we're going to need to simulate it as best as we possibly can, like a digital twin of the observatory and its output as best as we can. And that will happen eventually, the 3D high fidelity simulation. So, but DISRA right now is what we're using for the broad, low fidelity trade space exploration. And so I think it's a good place to start in pre-formulation, pre-phasing. Okay, and that's it. Thank you.
All right, thank you so much, Rocky. Do we have any questions for her in the audience? Thank you, Kyle. Give a round of applause to Kyle Cook from Louisville, University of Louisville, who's doing the online moderating. Questions?
Hi, I was wondering about the high fidelity science simulations and what kind of timescales we're talking about in reference to like the NCR and development stages of the initial instrument.
That's a wonderful question, which I am going to punt to John Zamer. I am totally punting that one to you because you tell me, man. I mean, obviously, a prerequisite for that is the integrated modeling of the observatory at higher fidelity, and we started working on that, developing it, but there's definitely more detail to be added to those before I think we're ready to do the really high fidelity 3D simulations. But you'll have to tell me when we have to do it. Yeah. Okay. Yeah.
Thank you.
Sure.
All right, one more round of applause for Aki. All right, next up we have John Zemer. John, take it away.
Hopefully this works. Hi, everyone. My name is John Zemer. I'm from the Jet Propulsion Laboratory.
What's going on?
I am the pre-formulation architect for the HWO Technology Maturation Project Office.
Same thing,
That's
just,
different. How many
Oh,
people have ever
did you
played that role?
like-
Right?
all right,
That's
tell
really unique.
Gary
At
to
the
get
end of the
offline.
day, I think what you're observing already in these 4 days that we've been together is we're doing things a little bit different.
Oh, I wonder if
Okay.
the camera.
When we build this observatory and we say this is
It's on
going to
camera.
be a community observatory, we really mean it. And that's intentional. Okay? And so I want you to understand that a lot of the work that we've done leading up to this point has been intentional. Okay, we're trying to keep this community as part of this observatory because we think that's the best way we're going to
He's
make
gonna
it.
warn me when he does this.
There's also some other practices that have come out of other studies that we're really implementing now in this early formulation or pre-formulation stage. And so my job has been to help with that and work with this incredible teams. I think one of the things that really is important in early formulation is trust. And trust means that you're honest with each other. Trust means that you're open. Trust means that you're sharing. And that's what we're doing. And so I really hope as we see everybody here and excited, and especially, man, I want to run through a brick wall after John O'Mara gave his closing remarks there. We're really working together. We want you to be a part of it. Okay, let's get started. Somebody hit can you go to slideshow mode?
I got it, John.
Okay, so how do we go from the decadal survey and everything that was in it? I don't know if you read it back to back. I have a bunch of times. There's a lot in there about what this observatory is supposed to do. Okay? So how do we go from that to this? There's a long journey between those two things, right? But a lot of those decisions about what that is get made early on without much information, right? How do we do that? Well, the answer is you. It's going to take all of us. This is a thing that is not a single person or anything. It's going to be all of us. And so how do we organize this? How do we get this group of people to really work together and come together to make some good decisions? Well, first of all, we have a lot of good instructions. And Aki and I think, absolutely share her vision about what DISRA is and everything. When we got together and started talking about it, so yeah, we gotta have that. I'll get to that in a second. She referred to the same thing, and I refer to the same quote here in the first mission study report, right? Design problems are baked into the cake at the start. But the decadal did even more than that.
Sorry. Yep. Try.
They actually have this diagram that has way more words than you could read, right? I'm violating the good rule of how to make a presentation by even putting this up there. Don't expect you to read it all, but there was a lot of guidelines that the decadal wanted to make sure that we were doing the job right. And so, click, please. So, we made a promise, right? We want to build that
What
truck.
part of
We
like
made-
is- there was another.
We are, we are going to meet, we are using the decadal survey and the SMD large mission study recommendations. Next, please. 3 real strong principles here. Next.
Trying. Okay.
Okay, we will use these things called concept maturity levels. I'll get to that in a minute. But it's a framework.
Because anytime
We're doing this early pre-formulation
Gives
work.
off the
We're going to engage the science and technology community. You are a part of this mission, right? We make a project office and we recognize that it's not just about technology maturation. It's about maturing the science. It's about maturing engineering. It's about involving the community. And then strategically invest in the critical technologies. That is the function of the project, right? The project will execute and will develop these technologies so that we can be ready to enter phase A. See, Can you guys advance for me?
Yeah, sir.
So, concept maturity levels. These are something that we developed at JPL a while back. And really it was a focus on our competitive mix. What we're seeing is that we had really incredible PIs come in and they wanted to develop their concept. And what we were seeing is they get a few engineers together and off they go, right?
Yeah.
And all of a sudden,
Doing
wait,
this.
you haven't thought about all aspects of your concept. You know, you haven't really dialed in yet. Maybe, you know, there's a really hard part here. You could use a different technology. You should get a subject matter expert in there, or that's way too expensive. That's not going to work. All those kind of things. So we developed these different stages. Cocktail napkin is literally what it is. It's you write the idea down. The only rule, the only thing is you share it, right? Then you're talking about initial feasibility. Now, interestingly enough, for HWO and Louvois, they got all the way to, you know, point design or even arguably a baseline concept. But then when we came together and said, okay, it's somewhere in between those two, we went back to say, well, it's feasible from these two architecture studies. We know that it's feasible. So we're already going to start at CML2. Next step is to CML3. We're going to enter the trade space. There's always feasibility questions. There's always trades to be done. It just depends at what level. So CML3 is about the architecture level trades. Okay. Next step after that is the point design. And you're going to see that these EACs, these architectures that have been designed, those two are designed to be 2-point designs that will continue forward. And then as we go to the baseline concept, number 5, we'll get down to 1. That's EAC 6. That's what we'll walk into MCR with. Okay. And then the other ones are matching along with project milestones, phase A, phase B, PDR, that kind of thing. So those aren't really anything special. The other aspect of the concept maturity levels is that there are 6 dimensions, not 2, not just science and engineering, but 6. One of the reasons why we're intentional about including the community is because story and strategy are part of what we do to mature a concept. Okay, it's not just the engineering, it's not just the science, it's also the implementation. We want to think about how are we going to actually execute this? How are we going to involve our foreign partners early? How are we going to involve industry early? Right? We don't want to wait. We want to have everybody in the mix here in this pre-formulation so we get it right. Okay, so as you go, the key thing here is don't advance in any one dimension past the others. If you do, more than likely, because some other constraint that comes from one of the other 6 is going to bring you back, and you're going to have to redo the work. So we move this out together. Okay, Lee Feinberg showed this chart earlier. This is intentional. Again, this is our process to make sure that we're trying to explore the trade space really well, to really involve all the different aspects and opportunities for people to contribute. We have these 3 architectures that we started. They were open designs, meaning that we didn't expect them to close. We didn't expect them to meet requirements because we didn't have requirements. But we did have is the 2 HWO and Louvois studies. And so we had a pretty good idea of what the science was going to be, a pretty good idea of what the instrument complement was going to be. We used those to keep moving forward. Now we're in this gray box here. We're almost done. Since the CML3 synthesis, that does not mean we have closed the trades. It just means we have opened them up. We're at this peak of ideas, peak of, well, there's always going to be more ideas, but peak of the idea that there are options on the table. We get down to 2-point designs, do more integrated modeling. This time they are going to close. We will come up with science requirements. We will make sure these observatories can achieve those requirements. That's going to be tough. It's going to lead to challenges. It's going to lead to questions. It's going to lead to the need to have that analysis tool so that we can come back and see what does this impact to the science when we change this parameter. Then we go down, we do a synthesis, we get down to a baseline before MCR. So we are not done, right? We are not, just because we have these 2-point designs means we are not done, right? We are absolutely still exploring trades. They're just at a lower level. Okay, next. Aki already really talked about this. The key thing here is that this is a way for us to quantitatively say, what is the impact on the science from an engineering change or an engineering challenge? And that's really what this comes down to. So Aki did a great job there with explaining all of that, how that works. All right, let's talk about another promise. Back in the 2024 January AAS, I said this, I had this exact slide up. This is what we're going to do for the next year and a half. We can understand and communicate what the ideas were concerted, what was studied and why, the science and technology drivers and challenges, key sensitivities, what happened when we vary key parameters and why, and the benefits and risks of each approach. And this includes documenting analysis, including the models and codes used to evaluate the performance, the soft spots, unique concept to the maturity, what technology, science, and programming. This is a huge amount of work. And the answer is we've actually hit on every single item. And you'll see that in terms of this conference is a showcase intentionally of a lot of that work. And it's not just by the project, it's by you mostly. Actually, it's by you, right? And so we're capturing that. We're bringing that in, okay? We've done a ton of modeling work. We've done a ton of design work. We've captured those key sensitivities. We haven't been able to share all that with you yet. Those are coming out in special data issues. There's a lot of work to go to really document that, and that's important to get it out to you. We've looked at the benefits and risks. That's how we sort of came to these new two EAC5s capturing, EAC4 and 5 capture the things that we've learned from this first trade space exploration. And then here we go. We're working still on a lot of these things, and these will just continue. They're not done. When you're at CML3, you don't finish exploring the trade space. You just get started. So it's still going. Okay. All right, let's look at this hexagon. Here's the proof, right? You saw Alice's talk. These are all the different components, all the different things that we've traded. This whole community has come together to share all of this information. We've got the science case portals that have all those science cases. Guess what? Those were intentionally written. You saw all these folks showing, well, I really like this. This is the breakthrough. But if I step back, that was intentional. That was so that we got to understand this whole rich science trade space. We want to hit the breakthrough on every single one we can, right? But there's going to be some tough choices coming, and we'll do our best to make sure they're informed choices, right? Then we've got our technology roadmap and the overall schedule. Aki was, I think we got a question earlier about when do we have to nail down the level 1 requirements? When are we going to do? Well, we have to walk into MCR with preliminary or draft level 1 requirements. We will have a set. They will, that doesn't mean that those things are rock solid in stone, right? We still have work to do in phase A and technology work to do in phase A that may influence what some of those requirements, the numbers in them. I think we'll know what the science is, exactly what number we'll hit. We'll probably be still working on. But, we'll be working with the CSIT starting now to divide, and you heard Jenya in her talk, in her summary talk, talking about identifying the key and driving science requirements. Okay, so this is sort of I'm also a manager in my spare time. So I do a lot of the, scheduling and budgeting work, but this is as consistent with what Scott was showing earlier today. So you guys can get a sense of the schedule. Got a couple of, about a year and a half, another year and a half here of work to get to those EAC 4 and 5s being complete, and then we start changing to the baseline. Okay, summary. We're at peak, openness, right? We got to keep that going. I think when I was reflecting on the question that was at the end there, what do you look forward to the most? I don't know about you guys, I love challenges. I love problems. I love the hard things. I love making really tough decisions with a great team. And so what we've got right now is a great team and a great community, and we're going to make these tough challenges. We're going to try to make these decisions as best we can together. So I appreciate your time. Thank you for your attention, and I'll take questions at this time.
This is actually
Thank you so much.
any questions for John?
People could hear, it's just if they're in the app or the browser, so it's not on us, it's on
Or
them,
online?
so they can hear. Yeah, then no question. See the speaker.
They can't see. This has to be plugged into.
Oh, what was the specific question? One more time.
So, yeah, we'll try this.
Oh, right. So, the way I think about it is that, with each different CML as we go and we progress, right, in NASA speak, there's a certain level of work breakdown. So with each one, we go another level deeper, right? And so with DISRA, we then match those things up, right? When we're doing the trade space exploration, it's that sort of 1D. Well, give us a sense about how much time this is going to take on an observatory where you don't really know how it's going to perform, but there's a lot of uncertainty there, but okay. Next level down, we have the point designs. Those are going to be much more specific. So those exposure time calculators will start to be a little bit more realistic, a little bit more time. And as we uncover where the real challenges are during that point design exploration, that's when we know where we're going to have the high fidelity models. So, and I would say in the next year or two, we will identify where we need them. And then certainly by an MCR, we will be enacting those high fidelity models because we have to show that this whole thing closes, that we actually meet the requirements. And so, we'll be starting it soon, but as far as when the results will be ready. Yeah.
Okay.
And then we'll keep using it, right? The idea is to keep using it.
So you just have to tell the makes application to listen to the camera, basically. Like,
I don't know how to do that.
Thank you.
you just switch to
So coming from my quite
this
limited
application
experience,
and
application,
start video.
let's say with flexibility is there in this timeline, like These dates are set
Do
out
you
for
want to set up now?
like over a decade.
Yeah.
Depending on how far this is going,
I'm
I
gonna
don't know,
take the
budget, like,
link,
how much flexibility is in there
Okay.
between whether it's the MCR or whether on.
when you go.
That's a great question.
For that.
The decadal survey said basically, and that's every decade, right? So they'll start their work towards the end of this decade. They said, look, no matter what, we want to know where you're at, right? And so in that recommendation, they said, you're going to come back to us and you're going to say where you're at. We think that's matches up well with what NASA requires for an MCR.
I need to do.
Okay, so an MCR, we're ambitious. We want those technologies to be mature. So we have a great MCR. We have a great idea of what this mission concept is really going to be. NASA actually requires us to be at Tier L6 at PDR, and they don't really talk about that early formulation. So there's a lot of flexibility there, but the large mission study said, that's not a good idea. Let's try to get more mature as early as we can, right? And so they recommended that we reach Tier L6 at the end of phase A, not wait until PDR. So there's a desire to move those things up. There's always, whenever you're in this whole regime, right, there's a whole bunch of conflict things, like you said, funding, right? All of that is contingent on funding. But at the end of the day, I think we will have the resources and the funding to do the work that's going to help us define those requirements, mature the technologies, the key technologies as far as we can. And then at the end of the decade, we're going to have a review no matter what, right? We're going to check in and and what we as a team really want to be is we want to be ready to enter into phase A after that. We want to be ready to start that phase A before the decadal makes its final, recognitions, maybe even at the beginning of that, right?
All right, thank you so much, John. All right, next up, we're going to hear from Matt East from L3Harris, talking about stable lightweight optics for HWO.
Thank you very much, John and Julie. So we've been working on stable segmented optics and telescope concepts and technologies for close to 8 years now. In fact, NASA kicked off all of these technology developments before the Habitable Worlds Observatory was even recommended by the Decadal Survey. So we got a head start, and we're going to show you what we've done with it, at least at a very high level. At L3Harris in Rochester, New York, we've been working on space missions, very ambitious, like the Habitable Worlds, for over 60 years. Since the first optical systems were put in space, we were involved with that. And ever since then, we've been advancing the technology. In fact, our history goes back to Eastman Kodak before this. So if you imagine to the left of this chart, going back to the 1800s, our gelatin plates were used for some of the first astrophotographs. So we've been supporting this community in different ways for close to 150 years. More recently, in the bottom right, you can see under universe exploration, we've been working on observatories in space and on the ground. So for example, Keck 1 and 2, Subaru, Rubin, the Vera Rubin Observatory. I don't know if anyone saw the first images last month. They were awesome. And we're looking forward to see the same in a year or two with Roman already. I can't believe how quickly it sneaked up on us. So this is all about the Habitable Worlds, though, and if the clicker clicks, this is what we're going to be talking about. So what do we need for Habitable Worlds as far as the mirrors? That's what we've been focused on very much, as well as the whole telescope. There's a few things we need. It goes a little bit beyond what's here, but these are the main ones. There's picometer class stable mirror assemblies. So the whole assembly has to work together to hold stable and maintain a stable optical wavefront so that we can get high contrast photography. We've done a lot of work on this. We've worked on stable mirrors and mounts and the assembly of them. We've worked on maintaining a stable and predictable environment with the Roman Space Telescope. Some of you may have seen Peter Miller's poster earlier this week, where we have results from RST in thermal vacuum that are traceable to tens of picometers RMS wavefront stability on orbit. So very exciting results that show we're within striking distance of what's needed for habitable worlds. We've also been advancing some stable mirror mounts and advancing technology readiness levels for those on the Ultra TM project. And we're continuing to do more work on the next phase of Ultra CT. The second item here is we need approximately 4 times better surface figure than the mirrors on James Webb. Now that's not a problem. We've done large optics, even larger than what's needed here, in that same surface figure quality. You combine that with some challenges for the edges. You got to get really fine quality out to the edges so you don't have large gaps between the mirrors, so you can get high throughput for the chronograph. And you put those two together, and there is some manufacturing development to be done, but there's no new technology. So we're on track, and we've actually started that manufacturing development on Ultra as well. The third item here is economical production of full-size off-axis A spheres. We've proven this. We have demonstrated large optics that are relevant, delivering them on 6-week centers. And we think we have a path with existing facilities to deliver them on 4-week centers. So if you imagine we need a certain number of segments to get a larger aperture, say 6.5 or maybe 8.5 meters, that's going to be helpful to be able to produce those optics in a reasonable amount of time and integrate them. And the fourth item here is properties for UV chronography. And we've been demonstrating progress towards UV coatings and low micro roughness that's needed to support performance in the UV. And we think that's also a manufacturing challenge. We think it's not really new technology. We think some of the coatings that Manny Quijada, for example, are developing at Goddard are very much ready and proven to a respectable TRL. And all that's to be done is to scale them up to 2-meter class and show that you can manage the uniformity on those larger optics, which we think is very achievable. So I'll dive into this first item, picometer class stable mirror assemblies. Here's a few examples. On the left, that's the Roman Space Telescope. On the right, that's the LISA EDU telescope. I mentioned the traceability to the type of stability we're looking forward to on Roman. We also, on LISA, we're looking at test results that University of Florida has gotten that shows our hardware is compatible with less than a picometer per hertz optical path length stability. It's a different metric, it's a different form of stability, but it shows that we're working to meet tight requirements on the picometer scale on multiple projects that are traceable to flight. On the Ultra project, we've made some specific new technologies, and a new invention here you can see in the bottom middle, one of our patents for a new mirror mount pad that's it's designed to be extremely stable. It's got a system of flexures that rigidly holds the mirror so it can survive launch, but the flexures also relieve the effects of thermal sensitivity and cure shrink and all of the other creep in the metallics, any other effects that could cause instability. But we manage that with this new capability. This is enabled by 3D printed Invar, which if you go down later today, you may see Steve Sutton's poster on additive manufactured Invar, which is much more stable than the commercially available Invar. We actually demonstrated this in the lab. We built a bond pads like this. I can't show them because of my compliance folks told me not to. But we've actually built these things and integrated them to mirrors and tested them in relevant environments in thermal vacuum. And we've got results like this. You can see these optical results with sensitivities well below 1 picometer per millikelvin. So we're starting to get very relevant results and advance the TRLs of these technologies. Another aspect is habitable worlds will need some control systems to hold it stable. And those control systems can only work as well as the measurements track what the optics are doing. So you've got these sensors that maintain the phasing, so all the mirrors work together as one aperture. And those sensors, how well do they track with the optical surface? Are they actually showing what the optic is doing? We're testing that, and we tested that in a similar environment. We're finding results where the shapes of what we're seeing is the exact same thing we predicted. There's some differences in the magnitudes, though, because when you go to manufacture these things, there's no such thing as perfection. You can't have a perfect, the drawing may say it's a 2 thou thick bond, but they're not all going to be 0.0020000. There's going to be some error. They're not all going to be perfectly uniform. There's going to be some wedge and variability from part to part. We're already understanding the effects of these aspects and trying to figure out, okay, we can fit those in the stability budget for habitable worlds. And yes, the sensors that are going to be mounted in these methods are actually going to track what the optical surface is doing. So we're making great progress there too. Fast forward to today. If we could jump to the next
Yep,
slide.
got it.
Thank you, folks. There we go.
Sorry.
It's okay. Oopsies. Okay. So one thing we're doing today is on TechMast. We're with Lockheed, led by Lockheed Martin. We're doing trade studies to understand what different mirror design parameters are going to influence the mirror response in the thermal domain. And what is the whole trade space and where do we want to be? Where are places we want to pinpoint? And in parallel on the Ultra project right now, you see a mirror picture in the top right there. That was a lightweight mirror core that's in process. That photo was taken 2 weeks ago. So this is active work that's going on. We're building 2 such mirrors, and we're going to be lucky to be the first in the Mini-Must Ultra Stable Lab to check out the performance of these 2 mirrors. And we're going to figure out how do they respond to thermal stimulus? Do they do what our models predict? And the 2 mirrors, what's different between them is there's one that's lighter weight and one that's heavier weight. So we can see with the heavier weight one, its advantages, it doesn't move much in response to thermal stimulus. It moves slowly. It's got a natural stability as a low pass filter. With the lightweight one, it responds very rapidly, which is great because it's very responsive to the control if you have a thermal control system. So we're going to be able to compare and contrast those 2 methods and actually show by analysis and tests that we understand how those mirrors behave. Fast forward, I'll speed up a little bit. Surface figure. We've demonstrated relevant surface figure on larger mirrors than this. This is a manufacturing aspect. This is not new technology. Surface edge effects. There's something interesting that happens for some large ground-based telescopes like Keck, Hobby Everly that we worked on, SALT, these 10-meter segmented systems. There's some challenges with, you have to cut down the glass, and there's some deformation to the glass when you cut it down. And that's how you get a very good optical edge. Usually when you're doing traditional polishing processes and grinding, you get these artifacts at the edge, which are undesirable, and they're not going to be compatible with habitable worlds. So we have this process to cut them down. Now the trick is, no piece of glass is perfectly strain-free. So any piece of glass you cut will change shape. So we understand that. We have models that predict exactly what the sensitivities are to the design. And we think there's some more work to show that we can do the types of optics we're talking about because these ones are extremely lightweight potentially. And we have a few steps here that we recommend going forward. The third item, the economical production of these large off-axis A-spheres. So we have developed this process called LTFCRR. It's low temperature fusion and capture range replication, whereby we take 2 thin plates and we attach them to a lightweighted honeycomb core structure. And we put those 3 together and they make an extremely structurally efficient, stable, and rigid structure that's also lightweight. Now, the benefit of the replication piece is that you can actually take on the form of an optical surface and furnace, and you can do it again and again. And if you're creating a great many optics, you can reach a certain figure repeatedly, and you can go from there to deterministic figuring, where we measure it, we change the surface with ion figuring or magnetorheological figuring, where we take away material selectively just to get to the perfect geometric shape for habitable worlds. And then eventually we converge within a handful of nanometers and we meet our specification and we move to integration. We've actually demonstrated making mirrors like that 1 every 6 weeks. So we have done this at a relevant rate, at a relevant scale. Unfortunately, those larger mirrors, they didn't let me bring them. That was another problem with our compliance team. But if you don't believe me, I did bring a little something sweet for dessert. So I'll just leave this here and folks can come up after, take a look and ask questions during the snack break later. But this last item is the smoothing that we've done on TechMast. We've been showing that, yes, we can make smooth enough surfaces. Yes, our processes are traceable to do that. getting down to single digit angstroms. And thank you to NASA and to Lockheed and BAE, everyone who's helped support us through the Ultra and TechMass projects. There are next steps. I'll let you refer to the D19 solicitation. I think NASA really did a good job laying them out there. And thank you very much to everyone who's supported, especially at NASA, and some more acknowledgements here. Thanks.
Thank you so much, Matt. We have time for one quick question.
We do have one online.
Great, go ahead.
R. Anastasia Erickson asks, when you say the HWO control system cannot address errors in feedback sensing, do you mean that it's a closed loop, but if the sensors are giving an incorrect reading, the control system can't tell, so the amount it tries to recorrect will be off?
I guess to clarify, I think habitable worlds can do that sensing. The aspect that's very critical is when you sense the location of these sensors, are you actually sensing the optical surface, or are you sensing something different? And if they don't track together perfectly, you may hold those sensors perfectly stable, but you're not holding the optical surface stable, so the wavefront may still be active in some way. So that's the aspect that you want to close the loop around ideally, and if they track together, then you've solved that.
All right, thank you so much. One more round of applause for Matt. All right, next up we have Elaine Carrier from Lockheed Martin to tell us about what Lockheed Martin's been doing for HWO technology-wise.
So we have heard a lot about ultra stability through that conference. There are many, and there's not one step way of getting to trust stability. It's going to take a number of strategies. That includes vibration isolation on the between the spacecraft and the telescope. That's going to take active alignment of the mirror surfaces. That is going to take wavefront sensing and control. And we just heard Matthew's talk here with the stability of mirrors. It's going to take some level of thermal control as well through the baffle. All of those things have to work together to get us to the stability numbers that we are shooting for in terms of dynamic wavefront errors on the order of less than 10 picometers, and line of sight errors shooting for 300 micro-arc second kind of numbers. So I'm going to take you through one leg of that journey, focusing on the dynamic wavefront errors and dynamic line of sight errors, and the vibration isolation portion of that journey. You can help me.
Gotcha.
So as part of that, I thought first I'm not going to dive too deep into the integrated modeling, but we have integrated modeling infrastructure that we are leveraging to do that work. That combines structures, optics, and controls, all integrated together and feeding into some of the coronagraph analysis as well, so that we get end-to-end performance. That infrastructure is a lot of it is parameterized and it's modularized in such a way that we can substitute models with others as we get new models, and that allows us to iterate quickly through the modeling process. Next chart, please. I'm going to focus on EAC1 for this presentation. This has been our test case for evaluating what kind of performance we might get with a vibration isolation system. So I'll take you through the modeling step first. There are two main bodies. One, the spacecraft with the reaction wheel and gives us the momentum control capabilities. And then the optical telescope, which I also refer to as the payload. So we have finite models of both of those bodies. These are independent ones, and we connect them through a vibration isolation system. And that's the part of that I will be focusing on. So there's the spacecraft structure itself has the first mode that's 0.048 hertz, so relatively low in frequency. The payload itself has that system has three functions. It provides payload pointing, uses the voice-coil actuators to apply forces to the telescope based on attitude correction requests, whatever those might be. Those forces are reacted on the spacecraft. And it has the other two functions is what we call relative position control and relative attitude control. Relative position control is based on information from the position sensors between the two bodies. And we use the actuators to basically maintain the system within its operational range, which is about plus or minus 10 millimeter at that interface. That is implemented in such a way that when we apply forces to reposition the payload relative to the spacecraft, we don't impart a moment about the center of mass of the payload and disturb the attitude in the process. The attitude control function, which is the third one, that one is using the position sensors to monitor the relative orientations between the two bodies, and we are using the reaction wheels to basically command the spacecraft to follow the payload in attitude. That's not something that can be done with the voice-coil actuators because we would get a conflict between the pointing function and the relative attitude function. Next chart, please. Skip one.
Gotcha.
Yeah, thank you. So of course that would be the ideal if we could be totally non-contact, no mechanical connections whatsoever. But in reality, we have to pass data. We have to pass power between the spacecraft and the payload. So we'll have some form of a cable unless one considers wireless data transfer or wireless power transfer. So I'm presenting here a case where for ESC1, it's envisioned that potentially we may need to pass up to 17 kilowatt of power across that interface. That's a lot of power. And so we did some primary sizing on what that cable, the power cable across that interface might need to be to get a sense that's factored into our analysis for the transmissibility of the vibrations between the spacecraft and the payload. So this shows here the actual frequencies that we are achieving, and I'm presenting it here for the rigid body portion so that, you know, it's not covered by all kind of structural dynamics and you can see what happens. We are implementing effectively a negative spring using the Bosco actuators and the relative position sensors to cancel the stiffness of the cable to some extent. We can see in this particular chart here, I'm showing a case where we have 70% cancellation of the stiffness. It's a negative springs that has also the effect of introducing significant damping into the coupled dynamics between the payload and the spacecraft. That actually, you know, that pre-compensations is what allows us to close the loop for the relative position between the spacecraft and the payload at a relatively low bandwidth, below the common frequency of the cables. Next chart, please. So this is the kind of vibration isolation that we are getting between the payload and the spacecraft. The important quadrant is the lower left on the lower right on the graph here. So what this shows is that in this section here, the transmissibility is effectively limited by the cable stiffness. That's what we are seeing. At lower frequency, we get additional rejections because of the attitude control loop based on information from the payload that basically cancels the effect of the cable at low frequency. And at high frequency, we are operating effectively isolation mode. You know, and by high frequency, I mean 5% above here in this case. And so we are achieving over 60 dB of rejections from the spacecraft vibrations to the payload at frequencies above like a few hertz. The worst case transmissibility is at about 0.1 hertz, which is at 16 dB, and 30 dB of vibration isolation at 1 hertz. Next chart, please. So this shows here the response of in terms of the wavefront error to the spacecraft motions. If you have vibration on the spacecraft, there's still residual vibrations through the cable and other effects that would come into play. So that gives us a sense of you know, how much the wavefront error is affected by spacecraft motion, both for the translation and the rotation. And the sensitivity is ideal for the transmissibility in terms of the translation of the spacecraft to wavefront error. What happens is that if you have a quasi-static acceleration, basically your anti-payload structure, you know, under that quasi-static acceleration has a static quasi-static deformation. Those quasi-static deformations at the 100 picometer per millimeter. That gives you a sense of you know, forces that we are talking about here relative to picometers. Okay, we need to get to a fraction of some of those numbers. Next chart, please. So these are time simulation results here. So this is a simulation case where I introduced some error imposed between the spacecraft and the payload. So what the system is going to do is trying to bring back the system towards the middle of its operating range. That doesn't have to be done very accurately, but that's something that goes on at relatively low bandwidth all the time. So you can see that the transient is killed relatively quickly. We have, in this simulation, we have both the FP system with all the control logic working. We also have a fast GME that helps with the line of sight stabilization. So some of the numbers that we are seeing in that simulation here, dynamic wavefront errors at frequencies above 5 hertz, at the order of 5 picometers, and 2.4 picometers at frequencies below 4 hertz. It's the kind of errors that we are seeing. Line of sight on the order of 1 millisecond. that's one place where I think we have an opportunity to improve that with the fast engineer. That's a question of dynamic range on the fast engineer. Next chart, please. So this gives you an idea where the activity is actually. Okay. So this is a spectrum, basically taking the wavefront error and doing a spectral analysis. So it's a multidimensional problem. I'm taking here the principal gain of that transmissibility, and you can see that most of the activity is in the mirror rigid body modes, which are in the 40 to 60, 70 hertz kind of numbers. The reaction wheel in this case, we have 8 reaction wheels. All 8 reaction wheels are at 3300 RPM. So I kind of put the worst case here in the middle, right in the middle of all those rigid body modes for the segments on their superstructure. And you can see the backward integrated IMS, where all of the in the system. Next shot, please. So this is a comparison here of the DFP system to 1 minute. Thank you. Comparison between the DFP system and the destruct system. So that's a classical, passive vibration isolation system resized here. So the same initial, the same conditions. In the other case, the vibration isolation will not isolated here. They are isolated. With the destruct, we are seeing errors at wavefront errors above 5 hertz at 60 picometers kind of numbers. Next chart, please. So there's a number of observations and lessons learned on this. So one is the natural frequency of the payload in the system at 10 hertz is significantly higher than what we have worked with in the prior iterations of HWO25, for example, when the natural frequency was in 1.5 hertz. Keep that. Okay, it's really important. It's for natural structures which are the 1 hertz kind of numbers. Testing them in 1G, very difficult. Here, with the cable stiffness that is across that interface, that basically requires more bandwidth out of the control system to achieve the stability. So there's decoupling between translation and rotation. It's very much a question of where the interface is relative to the center of mass of the payload. And on the AC1, we have about 3 meters. So coupling between translation and rotation is unavoidable, basically unavoidable. The closer we have the vibration isolation system to the payload center of mass, the better. There's some trade to do on the voice code actuators in terms of noise versus back EMF rejections, which is another source of transmissibility. Something that would actually allow us to bring some of those numbers down. So I'm going to stop here. Thank you.
Thank you very much. All right, any quick question? There's a question?
Hi, Robert, the Space Telescope. If I understand correctly, what you're saying is the payload can remain kind of stable and move without incurring some of the dampening of the spacecraft as it slews through the sky, right?
Is that okay?
If I'm understanding correctly, the payload is not connected to the spacecraft directly, so the spacecraft as it slews, you don't incur some of the dampening effects of the spacecraft slew on the payload.
That is correct. Ideally, if you had no mechanical contact, the spacecraft would move into the back of the payload within some limited range, plus minus 10 millimeter.
That which is 10 millimeter. Okay, that was where I was going to get to. Tracking. So the reason I bring that up is to ask this question, or to make a statement. On James Webb, we found we had a fine steering mirror that we could use to do partial slews about 0.06 arc seconds.
Mhm.
And
But we didn't know that when we were designing the science cases to do the dithers. And so the initial design of the dither patterns that we did with Miri and Mircam didn't take advantage of the much faster motion of the fine steering mirror. So this is another one of the good examples of if we know your data about how far you can move without incurring dampening settling effects, that will feed back into the science that you build that determines like how much motion we do in that. That's I would say that one.
This system could actually implement a dealer if you wanted to do that, you know, limited range, you know, as long as a degree or so.
A degree. Okay, that's
It's
huge.
it's not bad.
Like I said, in James Webb, it's 0.06 arc seconds.
Right.
So a degree is a lot.
Thank you very much, Elaine. Let's give him another round of applause.
Thank you.
All right, next up we have Shingo Kamida.
Thank you. My name is Shin Kameda, and I'm from Rikyu University in Tokyo and also in JAXA, from JAXA. And I'm a team member of their ISS HWO study task force team in JAXA, and I'm leading their activity on the UV ISPET technology. So today I'd like to introduce our activity and result. So on Tuesday, the Brian Flemings gave us a very good the lecture for the IFS, and also I think I can skip this explanation. But anyway, so MOS, multi-object spectrography, is good at scattered object, observation scattered object, and with a wide field of view, but it is scattered object. And IFS is a good at the continuously expanded object, so like I see moons or planets, and Mars and Venus and comets, and also galaxy. I'm a planetary scientist, but I'm learning the galaxy science knowledge. Thank you for this. And about high resolution spectrograph we are working on. And yeah, this is a very simple figure, but so this is the example of the optical design of the high resolution spectrograph with the HL mode. And this is the example for the Lapitar mission. This is a 60 centimeter UV space telescope study in JAXA. And in short, we have two gratings to get a wide spectral range and with a high spatial resolution. We have two gratings for the high dispersion gratings named HL and low dispersion grating called cross disperser. So to use the HL, high dispersion with the several orders and overlapped several orders, and to separate these orders, we can use the low dispersion grating as a cross disperser. So that makes the wide spectral range with the high spatial resolution. And so this is just one slide for the science case. And so about the transit spectroscopy for the upper atmosphere of exoplanet for Earth-sized. So this is, so in my understanding, this is not so intensively discussed this week, but I think this is very important. So I should know that. Yeah, let me do this. But so this is show the concept of the transit spectroscopy. So, but for Earth size, it is difficult, you know. So because the lower atmosphere composes the molecules that are sensitive to the optical or infrared range, either the optically thick, but the thickness of the layer, lower atmosphere layer, is very small. So this is very difficult to detect. So at this moment, it is. But let's see the upper atmosphere. So this is a image of the geocorona. Geocorona is mainly composed of the hydrogen emission around the Earth. And you can see that this black circle shows the size of the Earth. It is very small. But actually, the upper atmosphere is very widely extended around this small planet. And as a reference, I put the red circle. This shows the size of the TRAPPIST-1, the host, the example of host star. So in that sense, the upper atmosphere is not so small. But I should say that for Earth, it is the density is low at the upper atmosphere and it's very thin, so it is not detectable. But for the exoplanet around the low temperature star, in this case, even near the habitable zone, the XUV irradiation is much higher than Earth, and so that makes the upper atmosphere wider and with a higher density. So this is an example of, this shows an example of the estimation. So we can expect the very big atomic oxygen exosphere around the Earth-sized planet. And this shows the emission line from the host star. And this shows the transit spectrum. So we can expect a very large scale of the transit depth. It is detectable using the HWO, we think, for the oxygen atmosphere, even for the Earth size. Right? And there are several other studies for the hydrogen atmosphere. And so we can do the detection using the low resolution spectrograph. Even low resolution spectra can detect. But therefore, to know the atmospheric escaping process, key parameter is temperature. So to know the temperature, we need to know the shape of the absorption line. So we need a high resolution spectrum in this case. And there are many important lines, several important lines in the far UV regions, and hydrogen and oxygen, nitrogen and carbon. And also the NO2 and C2 is ions, nitrogen and carbon. So to cover this wide range and with the high vector resolution, we need a shell mode. So at this moment, so JAXA is start doing the study for the UV, IFS, and also the HRS in the one package like this. The size is like this. So this is 1 meter. So we have an image slicer and also the grating array and the detector here. So and to achieve the wide field of view, we separate the two parts, so 1 and 2 for the IFS. And the image slicer is not so big, so then we think that we put the light here for the HLS. So the size is smaller than this table. Then, so at this moment, our target specification shown in here, this way, in the FEV range, and the spectral resolution for IFS is about 7.02 nanometer, and the spatial resolution is 20 millisecond per pixel, with the width of 0.40 milliseconds. And FOV is so there are many requests, but at this moment we think that the 3 second by 3 second is feasible. And for HRS, we can cover the FEV range with the spectral resolution of 120,000. And this concept is very similar to the mission instrument for the large emission in JAXA, and because it also has an imaging spectrograph and also the high resolution spectrograph. So then we have in this study we assume that the size of the scope is 6 meter and the F number is 20, and this is target specification. And then our conclusion is we need 2 large size MCB detector and with a spatial resolution like this. And the point is 80 grade. We need 80 gradings. It is the number is very large point. And using this, we can put the 40 spectrum bar to this large size data. I think it's broken view, but so the side view is like this. We have a mini grating like this with the three row like this, and we so the light from the telescope comes to here, and we have an image slicer here, and we have our grating array here. Then we can make a 40 spectrum bar for one detector. That is current idea. And this shows our experience and also the heritage. The grating was used in the Hisaki mission, and also we prepared as UV spectra for the WSUV mission. So we achieved the relative diffraction efficiency about 60%. It is not bad. And we can achieve also for this number for the HWO, I think. And image slicer can be prepared by Canon. And so they said it is feasible. And coding is, this is under development. So we don't have a technology, because technology is very good. So we are trying to do the same thing to make a coding for this each optical elements. And next, what the key point is MCP detector. And so now we have a new technology for the MCP detector with a tapered surface. So we changed the shape of the surface and then increase the open area ratio and to increase the efficiency about 40% at peak in FUV. And so now we can make the 80 millimeter by 80 millimeter, but we need a 120 by 120. So this needs a technology development, but except for that, it can be feasible. And also the high resolution spectrograph, we need a cross disperser and Eshel breaking. So we can utilize the technology from the Shimazu, and also the Eshel breaking can have the same technology. We can use the same technology for the image slicer and also Eshel breaking. So we think in that point this is feasible in the product. So and we had a meeting last month about the IFS and HLS in Japan, and there are several requests from the Galaxy people and the planetary science people, and the request is go to get a higher spatial resolution, even with the now field of view, and others say that we need a wider field of view, even with the lower spatial resolution. And also MEV is important. So now, now I'm learning many things, but we try internally, I think. And HRS is necessary for the exoplanetary science, also the solar system science. And but we can reduce the spectral range to achieve the wider field of view. So recent activity. So other area-san, so area cable area introduced this morning. We just established the ISS H-level study task force team the end of last year. And the recently UV technology development program was approved in JAXA in June, and we start next month. So tomorrow. But in Japanese time, I found out it is today, so now it's started. Okay. Yeah, so then so it is in the program we will develop the large format tapered MCP with Hamamatsu, and also the high efficiency image slicer and grating. It is in the program, and we are discussing this company, and also the mission is under study, and down selection will be done in 2026. And the technology is common in this project. So then this will be the pathfinder for the HWO technology. this is last slide. And yeah, so so the Shimazu is a really relatively big company, and they know that JAXA is poor. I'm reluctant to ask them to prepare 80 rating, but they are very positive. I was surprised. But after that, so I knew their slogan, so that is in Japanese. So this one. So this is good policy. So I'm happy to follow this policy, but the requirement is. Thank you for listening.
Right. Thank you so much for that. Any questions? Online or in the room?
Hi, Singo. Very nice presentation. I have a couple of questions. The first one is, which is your evaluation concerning on the different technologies and the scattered light that can produce to get very dark images as a result, no? So to get the optimal contrast. And the other question relates to the possibility of making curved MCPs.
Spherical.
No, spherical or paraboloid. Yes, curved,
yeah.
with a certain curvature.
Okay, so first one, there's the scatter light of the grating. So yeah, we should do some tests for the Shimazu grating, but so the efficiency is very good. So and shape is very, so it is beautiful. So I can expect it is relatively low, but let me do this later. And the shape of MCP. So first we are trying the plane detector, so for the large format. But after that, so Hamamatsu has also experience with the spherical or curved MCP, so we can potentially we can do this. But at this moment, in design, it is flat.
All right. Any others? All right, let's thank Shino Kamide again. Thank you. All right. Next up is Christian Roy from National Research Council of Canada.
Okay, hello everyone. So last dessert before snacks. And after going to Japan, the previous stop, hopefully you still have your passport because you're taking an international flight to Canada. And if you get tariff on your way back to the US after this stop, we have nothing to do with it. My name is Christian Roy. I'm an astronomer, instrumentalist in high contrast imaging at the National Research Council of Canada, Erzberg Astronomy and Astrophysics Dominion Astrophysical Observatory Research Center. So challenge for the next conference to fit that on my badge. So we have a very nice research center. I don't have a laser pointer. Sometimes features in movies and TV series, so it's probably a very nice hideout for mad scientists, but it's very good architectures. The green building, we call it the Minecraft Creeper building. It's not exploded yet. This is our big integration facility, and inside there's a clean room where our instruments is located. So we have a NERC lab and an integration facility when we build instruments. So the lab is mostly undergrads, graduate student, and postdoc that are working on a lab, designing instruments, doing experiments. We started with Ben Gerard some time ago, and now we have postdoc like William Thompson, he's amazing, Adam too. We have a new grad student, we have scientists, optical engineer, mechanical engineer. It's a pretty fun team. We also have international collaborator. We're working with Subaru, they're amazing. The Skexio team, so we can bring our Pathfinder to Subaru to test our experiments, and also international collaborator that with Mamadou doing our chronograph design, and we're working with Fred Gramont in Quebec City at ABB for Fourier transform spectrograph they're going to get into, and also the Chaos group to fabricate our mask. So what are we presenting here? So what are we doing for high contrast imaging? So we're using what's called a cell coherent camera. It's basically a way to build a young slit experiment with a star. So you start with an entrance pupil. We have an appetizer, like an APLC chronograph. We have a focal plane mask at the middle. And we also then have a Leo stop. But the difference is we take part of the starlight, we send it off axis. So the starlight goes through two slits and the exoplanet light goes into one slit. And what you get in the focal plane is you get fringes because the stars has interfered. And if you study the fringes, you can actually derive the electric field of the photons, and that gives you basically the pupils, the entrance pupils, and all the aberration, phase, and amplitude. And you can use that to control your differentiable mirror or to post-process the images with a technique that we call coherent differential imaging. So a lot of students have worked at making this a reality, and it's super cool. This is a view of the bench, so it really looked like pretty much like a standard high contrast imaging instrument where we have an internal source at the upper right. We have like a telescope that can come in from the instrument where we have the observatory. We have two very good mirrors from Optimac that are a few nanometer RMS, the 208Es. We have an apero differential mirror of 468, and then an appetizer, focal plane mask. We have a Leo stop that we split the beam in two, one to a Sievert 2 that's doing the just the fringe tracking and the focal plane reference sensing, and the other light, the rest of the light go to a Fourier transform spectrograph, which is basically a Michelson interferometer. And the very nice thing about this is you can actually take images or data cube of your dark hole, but we can take it at R20,000 at every pixel. So we can derive the electric field, the phase amplitude error of your pupil at R20,000, which is pretty cool. And this is the instrument at bottom right. It's very compact. It's working air. And the goal is to study instrument for ground-based instruments. So the goal is to reach about 10 to the 7 contrast. And that's kind of the limit of what we can do with our differential mirror. So this talk is, we got this idea when it was time to submit abstract, is can we use this instrument that's 10 to the 7 contrast and just blast the detector with a lot of photon and try to post-process our way from 10 to the 7 contrast to 10 to the 10 contrast using multi-wavelength post-processing or coherent differential imaging, and going all the way to R20,000 and try to do something like what GB is doing with match filter or some crazy other approaches to really try to get the contrast to show that these techniques works, and if something happens in the habitable world, we can still safely get to these kind of contrasts. And this is important for NDES, PSI, and other ground-based instruments as well as habitable world. It's important to remember that spiders or instrument has not been designed to do this. So it doesn't have all the bells and whistles that like the GPL test bed or the Space Telescope test bed. But it's still quite interesting to see what we could do. Like I like to say to my student, we're spreading the wings of our spider instrument. Thank you, Chad, AI to generate these. So CDI, the coherent differential imaging, how it works. We have fringes, images that have fringe, not fringe. We have a chopper to turn these on and off. We extract the fringe information, you Fourier transform, you get two side lobes. These are kind of little pupil of your images that you extract, you Fourier transform these again, normalize the flux, and you reconstruct your image. Seems simple. This is basically CDI 101. You subtract and you find your planet at the bottom right. And that's basically how it works. So again, I won't spend too much time because I just have 10 minutes. We have an elaborated faceplate for ground-based instruments, and we rotate the faceplate on the upper right. So you see a lot of speckle, they're boiling. It's super cool. This is what we do on the ground. It's a habitable world, but if you activate the CDI post-processing, you're going to get the image to the right. So you see you have a lot of speckle, and poof, they disappear. It's like magic. You reconstruct the PSF with electric field, and you can then integrate this. So this is all lab data, and you're getting gain about a factor 40 to 50 close to the inner part of the PSF, which is pretty amazing. We're super excited. Say, ooh, we're going to show that this works for habitable world. We're all excited. We were, again, dreaming. This is, we're going to show this. We're in good shape. We have the Fourier transform spectrograph. Everything was working. We could extract data cubes to high spectral resolution. And then we tested CDI, the multi-wavelength post-processing. So this is an example where we had band mirrors at the beginning of the project, a lot of spectral information. We kind of simulate a methane spectrum from a gas giant, post-process it, gain factor 15 contrasts. Again, we said we're in good shape. We're going to make this work and get habitable world contracts. So I won't go through this, but basically what we said, we're working in the infrared. And we said, let's imagine that our images are instead in the visible at 760 nanometer, and we're trying to find oxygen on the planet, but using our images in the lab. So we closed the loop, built our dark hole to about 2 to minus 6 in these images. This is just the wavefront sensor imaging camera. We see there's a ghost. You see the dark hole, and there's a spot in the middle. So this is a ghost from somewhere we don't know yet in the instrument. It's a pretty bright ghost, 2 to the 5 contrast. And you look at the fringes at the bottom right, nothing is distorted. So this is incoherent light. So we said, no, a ghost, who cares? Okay. And we still have some good contrast. We can still process the images. So we activate the FTS and we take an R3000 of the dark hole, and I use the right slices to reconstruct the images that the other camera sees. And they look pretty similar, the same ghost. You say, well, okay, well, the dark hole is still pretty big and we can still try to get habitable world contrast elsewhere. So we decided to scan, and here are the images. And this incoherent ghost at R3000 suddenly is no longer incoherent and start interfere everywhere in our dark hole. So our reaction was, oh my God, what's going on? So then we realized that, yeah, effectively, this incoherent light at 1%, if you start increasing your spectral resolution, you're actually increasing your coherence length. And you can actually start resolving piston offsets. So if there's a lot of photon bouncing around and comes back to your focal plane, if you go to higher spectral resolution, you can now see interference with photon that's bounce around at longer and longer OPDs. And that's something we absolutely were not expecting, which I'm sure people at GPL and other knows about this, but we didn't. We were quite surprised. So basically what happened, if you had a pupil on the left and you send a photon of axis, create a speckle, and then another photon bounce on a reflection, internal reflection on an optics, bounce back and go back at the same location. It has a different length, a path length. It will interfere, and the longer the path length, the longer you're going to gain, and electric field will start to bounce around, up and down, interfere constructively faster and faster with wavelength, which we said, oh my God, this is so interesting. We're learning. And so basically, depending if you have coding errors, the goal that we're seeing here is about 100 micron OPD, which is pretty small. But the higher resolution, if you go to all the way to up 100,000, you could see interference from a photon that has centimeters to many centimeters of path length difference. So going to high spectral resolution could increase or generate way more problems than it could solve in some way, because you're seeing photons that are bouncing around everywhere in your instrument and starting interfering and creating signal that may look like biosignature when it's actually photon in your instrument. Yeah. So here's this quick simulation of habitable world where we cut our 3% filter in 3 band and said we tried to subtract, and what a surprise, it does not work. I'll skip that. And I said, let's go to R9000, because now we should see these Fraunhofer Fresnel simulation where speckle behave normally with wavelength and slowly move out with wavelength. So it takes a few seconds to start. Hopefully that works. We're expecting a bit more, too much wavelength than what it is, but basically we said, let's see what it looks like, and oh my God, you're at R9000 and speckle are boiling over the place. This is not what Fraunhofer and Fresnel is telling us. So what a surprise. Oh my God, the higher the spectral resolution we're going, the more chromaticity and the more crazy thing the speckles are doing. So these are 3 speckles. So this is a logarithmic scale. So you see some speckles have very big structure with wavelength, and some oscillate extremely fast. Extremely interesting. Then William, my student, said, okay, let's do something a bit like Jeep is doing, but something way more simple. We have 300 slices in our latitude. Let's assume the planet is bright in one wavelength and it's 0 photon elsewhere. And use all the latitude, all the slices except one to build a least square and try to subtract the speckle. So this is like this crazy optimal planet that's super bright in monochromatic light. And we're using the rest of the cube to post-process and subtract. Still does not work. We're getting about 4 times the 10 contrast, which is pretty good, but only again about 36. So there's a lot of chromatic information in there that we still need to understand. And if the good idea I had afterward is let's take this R 9000 data cube and let's take the derivative with wavelength. Let's see how the chromaticity, what's happening with the chromaticity. And we're seeing this wave goes around, which is basically seeing that, meaning that we have 2 wavefronts. So we have the science light on axis and the same wavefront bounce back and come back with itself with an angle. So here what you're seeing is the second wavefront that's inclined by about 4 arc minute and an OPD of 7 millimeters. So we actually think it's the window of our camera that has 2 wavefront interfering with itself. And then it's generating a bunch of chromaticity in these images. For time, I think I'm going to skip this, but maybe very quickly, since we can measure the electric field of the photons, you can actually take the Fourier transform of the derivative with wavelength of the images, and now you start seeing where the chromaticity is coming from, but with our phase and amplitude focal plane wavefront sensor. So the side lows give you images of the pupils, and you see we have a secondary obscuration with support, and inside the science beam, the chromaticity comes with concentric rings. We have not yet understood why this is the case. We see ghosts, and we can start seeing where the chromaticity is coming from, identify where they're coming from, and find solution. I'm going to skip that because I'm running out of time. We try CDI, does not work. Was working at factor 30 to 40 at very low contrast, high contrast, everything start to fail. We have saturated pixel, they mess around, we try to mask, does not work. All these extra ghosts and interference, they messed up our side lobe or reconstruction, they contaminate the central MTF. CDI does not work. Again, we were extremely surprised. We're going to have to work a lot harder to make these work. So we're thinking about upgrades to do better. So really, we have ghost problems. What do you do when you have ghost problem? You call it Ghostbusters. So Project Ghostbuster in our team has just started, where we're going to have a bunch of baffle and do our best to get rid of all of these photons bouncing around. We have Project Black Widow Spiders, which we're going to try to get better optics, get rid of all the glass. And when I see a Bertrand design for habitable world with a backrick and a polarizer in front of the beam, I won't have a heart attack. Oh my God, because this is really looking like our ground-based instrument and it's producing a large of mess. And so we're hoping to get rid of all that and try to get our instrument as chromatic as possible, and hopefully be able to show that in air with a very low cost instrument, we can actually get to habitable world level contrast by just minimizing chromaticity in the instrument. So I think that's going to be key for habitable world, is to limit these. So this is my new logo, spider and Black Widow spider. And we just submitted also a big proposal where we're hoping to upgrade our bench to be able to do a lot more research and get better chronograph, etc. And basically that's the takeaway, that ghost scattered light can really mess up your DM control. And if you're reaching the limit of your DM control, what's limiting you would actually also limit the post-processing. So this is important to remember. If you reach the limit of your DM, if it's generated by scattered light, ghosts, and everything starts to be incoherent or chromatic, well, SDI and CDI might also be limited. And all these effects, I think, also explain why if you build a dark hole at GPL or elsewhere with a monochromatic laser, and suddenly you say, let's try it in white light. And if you open the bandwidth, then all of these effects, these chromatic speckles start to appear. But with your DM, you can only correct one wavelength. So it means that you need to be careful with your chromatic errors. And so getting to broadband is not just about DM control or a better chronograph, it's also about scattered light control. With the laser, you have an infinite incoherent length, so your DM can do all the correction that you like. But as soon as you increase the bandwidth, things start to fall apart. So it's also a challenge about scattered light control and baffle and coatings and reflection, etc. I'll stop here because I'm sure I'm overly. Thank you very much.
Thank you very much. Right. Any questions for Christian in the room or online?
Sure, I'm following what you think the chromaticity is. You said something about it hitting the window. Actually, could be chromatic. It goes through the window. There's also like the fact that you could have multi-wavelength interference going on between wave, something that has a band pass. Go away from that center wave, you're going to start getting multi-wave. So what is the chromaticity? Or is it something else that I'm not explaining? Or do you not know?
So all this data analysis has been done in 2 weeks. So we're still learning and analyzing all this. So our current interpretation is really a wavefront that goes through, let's say, a piece of glass, a window, and then the window has an anti-reflection coating to try to optimize transmission, but then 10 to the minus 3 photons are reflected back. Then when you reach the first surface of the glass, then 10 to the minus 3 photons are reflecting back toward the focal plane, and then you have a 10 to the minus 6 wavefront that has an OPD that interfering with itself. Well, this is chromatic though, so depending on the wavelength, so as you move the wavelength, you change the OPD, and then the speckles start to move around and interfere. Yes. Yeah. Yeah, well, yes, but then you can have, you can imagine a glass or somewhere in your optic, and if you have some stability issues and the mirror does this, or the glass does this, you can change the angle of incidence of a scattered light ghost. Then when it's going to reach the focal plane, you could completely change the interference pattern. So, yeah, well, but this is what we did too. I mean, our optical engineer thought about this, and everything is wedged, and we still have a Christmas tree of ghosts. So we thought that we were crazy building an interferometer behind an interferometer, but nature was even crazier because we had an interferometer behind an interferometer behind an interferometer interfering with our interferometer behind our interferometer. So it's a mess. Thank you.
All right, any other questions? All right, let's give Christian a round of applause. All right, and this concludes the first half of dessert, and everybody has a half hour to let their stomach settle for the second half. I'll be back at 4:15 sharp. We are gonna go ahead and get started for our second half of our afternoon session. And first up is Rodrigo Zeladon from Lockheed Martin. It's all yours.
Thanks, good afternoon. I'll be going into a little bit more depth about disturbance-free payload, the concept that my colleague mentioned in the last session, and talking about the work that we're doing to advance this next generation vibration isolation and precision pointing system for HWO. We've heard all week about the stability needs for HWO and how attaining that stability is going to be extremely important to do the groundbreaking science that we all want this telescope to do. We've seen initial assessments that show that we're going to need line of sight pointing of about 0.3 seconds and wavefront error stability of tens of picometers over timescales of tens of minutes. And it's these low frequency payload isolation requirements that are going to be really critical to achieving stability that HWO needs. And that's where conventional isolation systems are not going to be able to meet these requirements, and where we need to adopt a different paradigm for doing vibration isolation. And that's where disturbance-free payload comes in. Disturbance-free payload is a non-contact vibration isolation and precision pointing system. It's non-contact in that when it's deployed on orbit, the spacecraft and the payload are physically separated. They're not touching except for maybe cables going across the interface. And it's by virtue of this non-contact operation that we get vibration isolation all the way down to very low frequencies. You can see on the plot on the right a comparison of DFP versus a passive isolation system, where DFP is getting significantly more vibration isolation at low frequencies and superior isolation across the frequency range. And it's a precision pointing system in that the payload reorients by exerting force on the voice coil actuators that are at the interface right here. And it's essentially pushing off of the spacecraft in order to reorient. That provides many advantages, one of which was mentioned in the last session. It's basically decoupling you from the payload, the spacecraft structure. The spacecraft structure has very low frequency modes. You don't need to wait for that full structure to settle before you can start your observations. And that's just one of the many advantages that doing vibration isolation in this way gives you. DFP is based on sensors and actuators that have significant flight heritage. So they're based off of hardware that's used routinely for fast steering mirror programs that are flying on orbit. And we've also been able to demonstrate the vibration isolation, the precision pointing, large angle slew capabilities, and the control system logic of DFP using our ground test beds. And so for those components of DFP, we're assessing them at a TRL level of 5 or higher. And then there's some work left to do in order to close the gap for the DFP system as a whole, to advance the TRL, the whole system to TRL level 5. And that includes doing these demonstrations with a flight-like software architecture and demonstrating contingency operations, things like health and status monitoring, and fault detection, and a fail-safe relatchable mechanism. Here we see some of the ground test beds that I mentioned. On your left is going to be the 2D test bed, and that's a test bed that has 2 air-bearing robots, and those demonstrate DFP in 2 degrees of freedom of translation and 1 of rotation. The one in the middle is our 3D test bed, and that's a spacecraft emulator and a payload emulator that are suspended from the ceiling, and that allows you to demonstrate DFP in 5 degrees of freedom. Show some videos of these. So you'll see for the 2D test bed, each one of these vehicles has a laser that's projecting on the wall, and there's some disturbance being induced into the
spacecraft vehicle, and you can see that the laser for that vehicle is shaking quite a bit, whereas the payload is very stable. And similarly for the 3D testbed, on the 3D testbed, you can see the arrangement of actuators. Here you can see the voice control actuators as the DFP system is operating. We're inducing some vibration into the spacecraft, and you'll see how we have a system that can also show that the spacecraft is vibrating quite a bit more than the payload. We've also been making improvements into the DFP system. We're working on this under the current TechNest funding. Here we're looking at reducing the noise from the voice coil drives. As I mentioned, these voice coil drives are based off of Heritage Flight fast steering mirror hardware. But we've been making tuning and adapting them to the DFP application, to the HWO application that allows us to reduce the current noise significantly, and that has a significant improvement on the total wavefront error. Simply by tuning some of the circuits, we're able to get a 2x reduction in noise, and then by tuning the bandwidth down to what the HWO application is going to need, we can reduce the noise down to about 0.3 microamps. We're also tackling the theta aquantization noise, which has a smaller effect on wavefront error, but we believe improvements can be made here as well. And then, as I mentioned, cables across the interface are the last mechanical connection between the two sides when DFP is operating. And so we're assessing how those cables affect our system when they're present, and they act as a shunt across the isolation system that can degrade the performance. So we're estimating what this impact is going to be on an HWO application. First, by looking at some of our previous programs where we've done test beds that measure the effect of cables on vibration isolation systems, such as the GOES-R test bed shown on the top right. And then also by looking at bottoms-up estimates of the composition of these cable harnesses that are going to be necessary to support the power and data requirements on EAC1. And then we'll be measuring the stiffness of these light-like harnesses in the next couple of months. And potentially we'll be investigating mitigation strategies to lower the overall stiffness and preload of the interface, and that involves careful consideration of the service loops, how we distribute this harness across the DFP interface, and potentially designing adjustability of the harness attachment points to reduce the preload. And you can see on the plot on the bottom right how the stiffness of the cables has a fairly sizable effect on the transmissibility of the whole system. Finally, to advance the TRL of this system, we are going to demonstrate we're going to close the gaps that I mentioned earlier by using our ground test beds to demonstrate flight-like software architecture. So that involves having representative interfaces between the spacecraft, DFP, and payload flight computers. We're going to demonstrate contingency operations, fault management and detection, health and status, and then we're going to have a mechanism that can relatch the payload in a way that is fail-safe. And these gaps can be closed in 2 years. And so we have a plan to complete that work. And I'll close by saying that we're very excited to be a part of technology development for HWO, and look forward to the years ahead to provide that link in the chain, as Scott mentioned, to get us to L2.
All right, thank you for your time. All right, any questions, either online or in the system?
Thank you. So earlier this week, we heard about needs of non-sidereal tracking speeds of like 150 milliarc seconds per second, pretty, twice JWST's tracking speed. Can you comment about, is a problem for DFP? Is it feasible? Or am I just misunderstanding how the technology works?
So the tracking speeds are going to be limited by how quickly the bus can follow behind the payload. So it's really limited by the reaction rates at that point. There's going to be some you have to take into account the settling of the structures too. So in that sense, DFP provides an advantage in you can have your spacecraft still have some, some vibration on the spacecraft, some residual vibration from low order flexible volume modes. And since your payload is stiffer, it's going to settle faster. You can potentially have that.
I mean, I think for this particular science application, we don't actually need tremendous stability. We just need to be able to track fast.
Any other questions? All right, let's give another round of applause for Rodrigo. Next up is Tyler Rock. Going to tell us about DMs.
Right. Hey, everyone. So I'm Tyler Groff. I'm presenting this on the part of a lot of people that are worried about deformable mirrors and getting them ready for the chronograph and testing them. Some of the main contributors are listed here. This whole deformable mirror development plan started with something we call the Deformable Mirror Technology Roadmap. And that was something where we all got together and we had a group of experts that in the field look at the HABEX and LUVOIR plans, look at what we've learned from CGI, and drafted some provisional requirements for the deformable mirrors, and gave those to the vendors that we looked through after we did an extensive survey. And we allowed them to react to that. They actually did a funded study, and we got development plans from them on how to get to the devices that we need. This is that group. I'm not going to go through all the names. This is up here mostly so that when you find that you didn't have a requirement or DM that you like, you're to blame. These are some of the vendors that we found, and of them in particular, there were 3 that were very close to meeting the technology needs of these devices. One is AOA Zynetics, who actually built the deformable mirrors for CGI. Another is Boston Micro Machines. That's an electrostatic technology. They use MEMS process, very different from the PMN. And then yet another one, which is electromagnetic devices from Alveo. So these 3 vendors, we actually handed these were, well, everyone can see the requirements, but these 3 vendors were actually given a little bit of money to go and do a study for us so that we can actually scope what a roadmap to getting to the device that we want will look like. And these are the basic requirements that we gave them, at least in some of our provisional requirements and performance. We asked for 96 by 96 deformable mirrors. We asked for actuator resolutions of about 2 picometers with a stability of about 5 picometers per hour. And then a total stroke of about 500 nanometers, which is for different technologies easy or hard. And then we also gave them a requirement of no bad actuators, definitely no pin actuators. Those are actually very difficult for a chronograph to chew on. So that's actually a pretty hard requirement. And as you can see, we gave them not just a requirement, but kind of an idea of when we're looking at these different design trades and things that we can do, how likely it is that we could relax certain requirements in different directions. And that was actually very important because that gave them the opportunity to say, well, I can meet this requirement as long as I can get a little bit of relaxation over here, right? So that gave us a conversation with the vendor. I think that was a very, very important part of getting this plan that we're talking about put together. This is a little bit of an eye chart, somewhat intentionally. I'm not going to read the whole thing, I promise. But the point is that the DM requirements are written as, are considered as a system, the electronics and the device. And we've got to get both of those things to TRL5, to playing TRL5 for deformable mirrors. And so, but the important thing is breaking down how we do this conceptually in the flow so that this isn't a completely serial activity and it takes 20 years to do. So the job of reaching TRL5 on the electronics is to prove that they can provide the drive that the device needs to meet those requirements that I showed you earlier. Whereas for the DM verification, we want to prove that it can respond and behave, assuming that it has sufficiently good electronics to operate in. And so by breaking it down that way and decomposing that, we can actually work on those TRL raising activities in parallel. And you can use, for example, TRL4 electronics or breadboard electronics to actually verify a TRL5 device, and then allow the TRL5, well, the development of like an ASIC, for example, for a TRL5 device to go in parallel, and then those two can get married and introduced into coronagraph testbed verifications. This is a little bit more of a kind of detailed breakdown of how that flow could look, or how we think it should look. And I broke this down into the technology development flow, the TRL milestones, and then how those for the device and the electronics, and then how those are feeding into the coronagraph instrument TRL verifications. And the main takeaway here is we're scaling up along the way. So what you'll notice is that we're not doing TRL5 coronagraph verifications with the 96 by 96 DM necessarily. We want to do that with 48 by 48s and 64 by 64s that we've developed along the way, so that we can actually make some good progress and appeal to the scalability rules of TRL5. So that's how you get this into reasonable scope, because spoiler, when we asked them how long it's going to take to get to 96 by 96 TRL5 DMs, pretty much all vendors said beyond 2029 or 2030, which is not really what we want. So this is going to be a very important way of doing this, so that we can actually meet a reasonable schedule and buy down risk on the DMs and the chronograph. We didn't just hand them technical requirements and then said, go do your thing. We're actually talking with them and engaging with them about how to actually get through a full qualification program, which is very important because we have very strict requirements, some of which are on the bleeding edge of even our ability to measure them. In addition to thinking about what requirements we're giving the DM vendors, we're thinking about how we're going to measure them in the first place. So picometers in a lot of places, right? So it's pretty tough. The thing, and part of that is we got to remember that they're DM manufacturers, they're not optical test facilities. So we have to help them and engage with them and work with them directly to actually get these devices to where we need them. None of the vendors are really interested in building electronics necessarily for flight, and they're certainly not necessarily wanting to do picometer verification, build up picometer test beds in their own facilities. Them to help support by analysis. And in this, I can't stress enough, something that we learned in CGI, something that's going to be a mantra for HWO's integrated modeling involvement in the early device performance evaluation cycles is going to be important. We need to actually trade the requirements for the whole system, not just the device. We will fail if we just strictly give the DMs hard requirements and don't flex. So that's going to be very important. Also important, as I said before, was those intermediate deliveries. 64 by 64 devices earlier in this development plan is going to be super important. If for no other reason than when we try to get to 96 by 96 in the future, we already know we can make a 64 by 64. So that helps with potential graceful descope options. And then, of course, we have to, just like anything, we have to be very careful and pay attention on backstops for supply chain issues. These are very boutique, specialized devices that use specialized facilities, and we need to make sure that continues to exist through the life of the project. Some risks. We did also do some risk assessments in this whole plan and what we provided in our reports. Here's some breakdown of some of those. We actually are, it's definitely technology dependent, but some of the ones, and I didn't want to pick on individual vendors, but these are like kind of an aggregate of all those things that some are susceptible to actuator surface drifts that we may not actually get to where we need for stability. Bad actuators near the edge of devices, can be a very problematic thing, and that's definitely something that we maybe not, well, it's possible we won't be successful with in the long run. And that's a particular problem if you're trying to tile to get up to our full format. Surface and actuator print through is another one. We really need that pristine surface quality with no print through of the surface. Any quilting or any surface topography really kills the chronograph performance. And then thermal loads is another issue. Some devices put a lot of power, take a lot of power draw, they put a lot of heat load. Managing that and actually keeping it low in the first place is something that is definitely a technical risk associated with these devices, or at least some of these devices. There's also risks on our own verifications. One is that the outer working angle that we get with the large format DMs, there's a gap there in the technology development plan with the chronograph. We can't do that with the smaller format DMs directly. We kind of have to build up to that. And then requirements on the DMs. There's always this one, right? Maybe we have a requirement that should be more strict than what we're planning right now. I'm looking at you, Ultraviolet. Picometer verification of DMs is also going to be very challenging. This is becoming less and less of a risk as we move on, but the fact that we have picometer verifications and temporal scales that range from 50 hertz to an hour or 10 hours to do that makes it really hard. And then finally, many years, it's going to take many years, as I said before, to get testable devices. So it's just a really hard, long development path. So we're going to have to be prepared for that. And I think, hit the double tap here, sorry. So anyway, with that, here's some suggested future work and trade studies. I will say we need to consider what intermediate milestones we can have to buy down risk, such as getting 64 by 64s in the development plan. That'll stretch out how long it takes to get a 96, but then we'll have a 64 to use. Electronics design, that's a major CGI lesson learned right there. We've got to work on that and get the ASICs together. Again, something that's getting better and better, and I'm becoming less worried about it. This one I can't emphasize enough. We need to allow for system level trades on the DM specifications. We need rigorous requirement decomposition from payload all the way down to these devices, and have a close tie with integrated modeling so we can truly trade performance at the observatory level. We have to know, as we're developing these devices, if they really are doing what we need, and if we can allow certain relaxation along the way. And then we also, again, we're not keeping them in a black hole. Including quality assurance and mission assurance in this whole process early and working that is very important. When we did that with anything on Roman, getting the coronagraph people to think in Q, and I can point at myself here, thinking in a sense of QA and mission assurance takes time. And so we don't want to do that at the last minute. And a lot of these vendors have never done a full project. They've made deformable mirrors, not rockets. So then we need to also, I think, reconsider how we define stability and precision requirements. Right now, we've got these picometer numbers and they're held at single actuators. But actually, when you look at the requirements we wrote down and we sent to the vendors, you've got almost a coupled power spectrum in space and time that you really want to verify. And I think if we start thinking about it that way, we should, and actually write that down, we can think about ways to test that and verify that in an aggregate way. And so that's actually maybe somewhere where we can consider some different facilities and verification methods to complement the ways that we do it now. And that will certainly help with the time on things. And then finally, we had laser focus on getting that hard one done, 96 by 96 DMs. But what we also need to do is do more rigorous studies at the instrument level in pairing those high order DMs with low order and parabolic deformable mirror devices that have lower actuator counts, but can maybe be used for beam stabilization in faster loops that take some pain off these high order DMs. And once again, allows us to relax some requirements on them so we can get them through the door. I think that's all. Thank you.
Thanks so much, Tyler. Any questions for Tyler?
Yeah, so thanks for the clearly laying out those top risks. I was eager to see your ideas for mitigating them. And because what you've written here is future work, but it wasn't exactly a mitigation lined up with the risks, the specific risks.
Yeah, so, so some of that is because the vendors all gave us plans on how to do that and develop that. Those are competition sensitive documents, so we have to be careful about where we go.
Oh, okay, all right, fine.
Yeah, but they are there, and these are the ones, and there's more than this, right? There's other things they have that we needed to get the device that we need in the end. These are the top things that we think are going to be really hard.
All right, any other questions? Okay, let's thank Tyler again. Oh, Elaine.
So as part of your effort, have you looked at using the DM for doing feed-forward composition?
Yeah, and that actually is what I was alluding to with the low order work, like the low order DM, so that there's some interesting device quirks. These things they all have their funny little quirks. One of the things is some of the devices have some drift after you apply voltage. And so you don't want to feed forward things from external telemetry because you want the DM to sit still. And then there's also just like with pretty much all of them, there's a state dependent gain. So it's in theory possible to deal with this, but it's really hard to. But what you need to do is feed forward that command onto the surface and but either account for or not mess with the gain so that you don't mess up the high order control that's keeping the dark hole maintained. That's the hard part. And so putting another device in there whose job is to do that is really what I meant by relaxing requirements on the DM.
So is that driving the range in any ways?
Sorry, range?
Yeah, the dynamic range.
Oh, interestingly, when I wrote down the error budget for strobe, I expected the telescope to give me a very difficult number, but they didn't. The driving number actually was the various coronagraph types that use the DM to do some phase apodization. That tends to be pretty large stroke, and so those end up chewing up a good chunk of error budget. That was a surprise to me.
Where do you see the biggest bang for your buck in the technology development?
In terms of like
Number of things that you're saying that future work that you want to do.
Oh, yeah. I mean, certainly the verification side of things, but I think in terms of bang for your buck, I mean, I would be going after buying down these risks, because you look at these plans and one thing doesn't fix one risk. There's a lot of things that have to happen, and they're all interconnected and they fix all of them. And so funding those things, like for example, doing something, working to get the surface topography brought down. There are very clear papers and demonstrations that show that if you have a certain level of surface topography, you have no hope of getting the contrast you want in broadband light. So that's an immediate flag, like we got to do that first. And that's something that I would say we want to fund, very quickly. I mean, I want to fund all of it, but that's the kind of thing that bang for your buck is whatever means you don't get good contrast.
All right, let's give Tyler another round of applause. Next up is Jesper Stockveld from the Open University in United Kingdom.
Hello, yeah, so I'm Jesper Stockveld from the Open University. I work on detector development, and we've been looking at HWO and future missions detectors. So I work at the Center for Electronic Imaging, which is a collaboration between Teledyne ETV and the Open University. So we do work on a lot of missions, Gaia, Euclid, and so on, and we do everything from radiation environment and those simulations, detector test, development and tests, flight device characterization and delivery and into post-launch calibrations. So the work I'm presenting here is initially funded through the Castor telescope mission. I hope you saw John Pastor's post earlier. So this is a UV mission with 3 bands from 150 up to 550 nanometers and sporting 3 large focal planes using the CIS-300 and 3 Teledyne E2V detectors. But these detectors and this work fits very well into HWO instrumentation, especially the Pollux mission, which we're part of. Caroline Corey-Niner gave a presentation yesterday. And of course, as you heard earlier, today the UK is very interested, very keen on delivering an instrument, and this could potentially be an imager, high-resolution imager, where these detectors also go in. And there are plenty other instruments where these detectors could be used. So it's definitely something that hopefully there's a lot of interest in. Nope. Yeah, so of course the initial problem is to detect the UV photons. And I know there's been talks from Shuley and Michael Henk earlier this week, but just to recap, then the problem with detecting UV photons in silicon is that they have a very short absorption depth from like about 400 nanometers down to about 100. And also silicon has a very high reflectivity at these wavelengths. So you need some sort of technology that will allow you to get the photons far enough into the silicon to be detected. So this figure on the right will shows you if you don't have any surface technology on, the photons will get stuck in the upper layers of the device and will recombine with the surface and therefore not go in and be detected. So what you can do is you can put a boron implantation very close to the surface and thereby creating a potential well that sort of pushes the photoelectrons into the probe channel. So Teledyne E2V has their own UV enhanced coating where they put a boron implantation in using low energy boron implantation, and then that gives you a dopant that's about 40 nanometers in, and then by doing an etch of the surface, you can then reduce that depth space or that layer where nothing is, where photons will recombine with the surface. JPL, as you heard, there's a dope technology where they use the multi-layer beam epitaxy to put this implant very close to the surface, a few nanometers in, which of course improves the performance. So we've been doing some tests on the quantum efficiency, but also on the manufacturability of these devices. Of course, the UV enhanced coating is part of their flow, and have been used on missions before, whereas the Teledyne is working with JPL to improve their or get their process into a way into a state where you can deliver fully deliver flight devices to missions. Work now? Yep. So we've done some quantum efficiency tests. We went to the PCB beamline in Berlin. They have a 40 to 400 nanometer beamline, and we tested these two technologies against each other. And as you can see, the two coating technologies perform very similar down to 220 nanometers. And below that, you see a clear improvement in the delta dope devices. As you say, the delta dope device had because it was a device that was meant for the Castor mission, so they put the coating on, which was optimized for the Castor UV waveband from 150 to 300 nanometers. So that's why there's a bit of a cutoff at 150. And also these results are not corrected for quantum yields. The fact that at very high energies or short wavelengths, you get more than one electron pair per detected per incoming photon when it's detected. So JPL provided me some calculations of transmission. So the green curve here show the calculation of the silicon transmittance of this Castor coating. And as you can see, there is this curve is slightly lower below the 220 nanometers, and this can be attributed to quantum yield. But it's much lower than other studies have shown. So there's a lot of JPL and CI is doing a lot of work on understanding the quantum yield. So because that's important, if you detect X number of photoelectrons, how many photons there's actually coming. So the tests were done at -30 degrees. So we've got a setup in our building a setup in our lab, and we've done some initial tests that show that we can go that between the -50 to 25 degrees. We find that the delta dope coating is very stable. You don't see a change with temperature, which is good. Of course, the important part is you need to have large area detectors, and as most people probably know, the CMOS detector technology are slowly replacing the CCDs. You can get faster readouts. There's a lot of you can do a lot of things in the pixel, and there's you can do on-chip digitization, which gives you simpler readout electronics, and you can they usually run at lower voltages and therefore lower power consumption. So Teledyne E2V, we've been testing this or started to test this 300 detector family. I'm not going to go through everything, but it's a big 9K by 9K device with 10 micron pixels. There's a lot of modes, high dynamic readout, where you read out with both high and low gain, so you can get low noise and a high full well. It's a radiation hardened device, and there's also a deep depletion device or version where you get better red responsivity. And there's a poster by Dr. Jordan. I think it's only online, so go and see that if you want more details. And there's also some initial tests from E2V. So as Belitech would say, luckily Teledyne doesn't produce perfect sensors, because that means that we have a lot of work on testing and characterizing these devices. So we built this test setup with a big vacuum chamber. You can see the device mounted in the middle there, which will allow us to go to take the device to beamlines and UV testing, and do radiation damage testing of the devices as well. So we're started doing electro-optical characterization on a lot of different parameters to see how well this device operates, and trying to understand it in as much detail as possible. The device, because you can control both the pixel charge conversion And there's the ADCs that converts the charge to a digital number. There are thousands of settings, and you can adjust almost everything with this. So the plan is to optimize the run. So we want to get the noise even lower than the promised 2 electrons, hopefully down to about 1 electron. But also figuring out what is the best way to run this device for different science cases. So if you have a specific science you need to do, need to run fast, slow, whatever, how do we optimize the performance of the device? Yeah, and then as I said, we're planning on doing a radiation damage campaign of this detector. Yeah. And you see at the bottom here, we see our UV characterization bench that we hopefully can get down to 120 nanometers light convert. So the last thing another thing we've been working on is the photon counter pixel. So there's been some whispering over the week that there might be a coronagraph on the Habitable Worlds Observatory, which will need photon counting devices, but also for a lot of the UV technology, especially if you want to go use this detector to go down into the mid and far UV, where there's could be very few photons. We need photon counting capabilities. So an old method is the skipper method. This is implemented on CCDs, where you add an extra floating gate. And then you basically measure the charge many times non-destructively, and then you can drive down the noise with square root of the amount of measurements. However, for a CCD that only has one readout, this of course takes a lot of time because you need to do often many thousands of skips or measurements. So what we've implemented is to implement this floating gate in the single pixel. So if all the pixel has a skipper capability, you can speed up this process by thousands of times, because you can do a skipper for a full row at a time. We hope that will give us a photon counting capabilities with the SIS300. We have a prototype device that's been produced. It's currently, I think it's been delivered to a lab, and we'll be starting testing that very soon. The hope is that in future versions of the SIS300 device family, this can be implemented as another mode of operation, so you can do many different things depending on your science data. So that was all for me. Just to recap, the detectors are backbone of all instruments, and it's often one of the cost drivers. We need to improve the UV technologies, and we hope to make make silicon far UV detectors possible. We're doing the SIS300 characterization and the photon counter pixel. And as this is a international collaboration session, I would say that we're always very interested in working with you on your instrument designs and proposals. So do contact us if you want to have input on the detectors. And now to the most important part of my talk. We're currently hiring 2 positions at the Open University to work on H2O detectors. So if you want to escape all this heat and wetness, you can come to the UK. It will still be wet, but it won't be as hot. So, do come. That was all for me. Thank you.
Thank you, Jesper. Any questions online or in?
I think so. I also happen to work with CMOS single photon counting detectors. They're from BA, but you're not going to like this question. It's about quantum yield. We're also trying to measure it, and we're having some trouble. We're using the photon transfer conversion gain method, but I'll just say we're getting some weird results. So do you have any plans forward, or are you going to use the same method? I'm curious about your idea of how to quantify quantum yield.
So this is something that KPL has done a lot of work on, and we're going to try and do the same. I think you can do PTCs and that kind of methods to measure it and get a good understanding of how that works. But it's not simple. What I understand is that it's very device dependent, and therefore it's not like a one size fits all kind of thing. So it does take work, and it's something that needs to be probably characterized for on a detector basis. Okay.
Anyone else? All right, let's thank Jesper. All right, and next up we have 2 consecutive remote presentations, starting with Jerome Amu. I'm sure I butchered that name very badly. I apologize.
He's got it.
Good afternoon. Can you hear me?
Jerome, go when you're ready.
Okay, thanks a lot. Thanks. I'm Jérôme Amiot from CA France. I'm a system engineer in Space Instrument, and I'm presenting a European proposal to contribute to HWO in the form of high precision and high accuracy astrometric instrument. So I'm not going to come back on the importance of
Hold on, Jerome, we
astrometry.
can't hear you. Give us a moment to
Okay.
try to troubleshoot this.
Sorry. Can you hear me?
Jerome, I'm monitoring and I can hear you.
So this is about this hot exotic dust. It has been found around 20% of the main sequence. Diverse,
Hear me better?
diverse stellar ages, young stars. It has also been found around
I think the room
So
is
is it okay?
1 second, please. I'm not in the room. I'm remote.
Okay, so I'm not going to come back on the importance of the astrometry to determine the mass of exoplanet for HWO that has been presented by Fabien yesterday. I'm just going to highlight the driving number and the science case that we use for designing the instrument, which is detection of exo-Earth astrometric signal at 10 parsec. So this is this 0.3 microarcsecond signal, and with an assumption of signal to noise ratio detection of 6, then the astrometric noise at the end of mission that is allocated is 0.05 microarcsecond. So we are building a sequence where each target will be observed approximately 100 times during the survey, so that we are designing an instrument with single astrometric error of 0.5 microarcsecond. So just a reminder that we are not talking about absolute astrometry, but relative measurements of angular displacement of the target star in the reference grid set by the calibration star that are close to the target. So we have broken down the single error allocation of 0.5 microarcsecond between 2 major blocks. So the first one, the yellow block, is the accuracy of detecting the photocenter of the stars, both the target and the calibration stars. That's approximately 1/3 of the full budget. And the blue part is really the bulk part of the allocation, is once we have the barycenters in pixel space, how do we bring it back onto the sky in angular measurements so that we have the astrometric signal. So we can see that all those values are below microarcsecond. So we are obviously talking about a calibration mission. none of those performance can be reached for hardware only. So the first part is really the budget in the accuracy of the star photocenter determination. And this is mainly driven by the PSF size and the photon noise. So it's driving at first order the parameter of the instrument: focal length, the pixel size, field of view, integration time. So with HWO, we'll typically observe a target, which is a magnitude 5 target. This is the target on which we want to detect the exoplanet. And we will have about 20 to 30 calibration stars that allows us to build the referential grid for the relative measurements. So what we have seen is that with the current design, in an observation of typically 2000 seconds per observation, we would be able to meet the allocation that we have put to this astrometric barycenter accuracy. The next part of the budget is really the whole calibration budget error, because we really want to transfer from the pixel where the detection of the barycenter is done onto the sky, also on angular astrometric measurements. And that's done in 2 steps at the instrument level. The first step is from pixel space, where the measurements is done, to the telescope focal plane. So we are still in the metric image focal plane, and we need to calibrate the pixel grid. And then it goes from this telescope image focal plane to the entrance angular value, so the astrometric values. And this is really the calibration of the optical path, so all the distortion, if you want. Both allocations you can see are at the 50 micropixel level. So this really requires some strong and solid calibration plan. And we're actually also working with hardware in the loop in laboratory to validate the numbers that we can reach after calibration. The first calibration part is calibrating the pixel grid. So we know that the pixels, they are not perfect top hat grid due to manufacturing, intrapixel response variation. So on board in the instrument, we will have a calibration unit which allows to retrieve the pixel grid by projecting interference fringe pattern on the focal plane and scanning them on the focal plane. So basically, it's pairs of fibers that are fed by laser and that project young fringes on the focal plane. And we scan those fringes with a modulator. And this allows us to reconstruct the pixel grid. So the calibration unit will be located on the PLM, but the fiber pairs will be located in front of the focal plane. So there is already ground demonstration of this technique and this principle. You can see a poster that was presented by Manon Lizana from IPAG, where there are test beds at IPAG currently testing this technique. The performance level at the level of allocation have already been demonstrated on ground. There are 2 papers, one in Europe, one at GPL, which shows that the 510-5 pixels can be reached by this technique. But we carry on upgrading this test in order to apply it to the HWO CMOS matrix that we're going to use. The second part of calibration is really the calibration of the telescope. So the optical propagation from the image focal plane to the entrance of the telescope, an angular dimension. And we know that the centroid of the PSF will be affected and will be affecting the astrometry even for minor wavefront error change. For example, when the footprint of the optical path moves when you change the field, or due to surface from error polishing. So there are analytical demonstrations that the current allocation can be made, but we are working on building a calibration approach specifically for the HW case. So this is a big bulk of work ongoing to be sure that we can reach the allocation for the telescope calibration. Of course, we're going to be helped by the extremely high stability of HWO, but still it's a very demanding calibration that we are willing to validate. So the implementation of the instrument that we're currently studying, there are two possibilities for the implementation. There's a trade-off ongoing. One is at the HRI focal plane, so the high resolution imager camera focal plane on the UV's side. And one
We have a backup presenter in the room who's going to finish the presentation.
Constantly, I'm working with Jérôme, and I hope it will connect again and rapidly because it's not my skill. So if I have no slide, that will be very difficult. So two possibilities, either at the focal plane, HLE focal plane, or on the two slots named guide at ESC3 guide. And of course, we prefer the second option. The baseline selected dedicated instrument at the guide ASC3 is under study. And it could cover a form with 220 megapixel CMOS with a pitch of 4.4 micrometers to provide detection of calibration star with a magnetic range between 15 and 20, and one small sensor in the middle, which is a 14 megapixel array, which with a two redundancy, which provide a detection of target with a mag range of 4 to 7. Yes, you can see. I think that Jérôme is moving the slide. No. So
Help me.
You don't know. Yeah. Calibration unique fiber will be located. Yes, is moving. And here you've got the final assessed preliminary design with the focal plane, the fiber assembly, which has been assessed with a total volume of 250 millimeters per 200 millimeters per 350 millimeters, about 20 kilograms for the FPR and 15 watts, interfacing at the FGS telescope plane. This FPA includes 4 pixelis CMOS detectors, Giga 220 megapixel and 3 Giga 14 megapixel. And you've got a laser calibration assembly, which has been assessed at 8 kilograms for calibration unit and about 20 watts, which is under development at Grenoble, which will be located at the PLM with a routing on fiber around at the last terminal, which represents about 600 millimeters of optical fiber. The focal plane detector is a key part of the focal plane. It's made of 4 pixelis CMOS detector, which represent 1 billion pixel with a pitch of 4.4 micrometers. They are under development by Pixelis. They have developed a 46 megapixel array, which is under test at Grenoble, and it's just an extension of this 46 megapixel array. The main particularities are field of view of the camera is 4 per 3. The quantum efficiency will be above 50% in the range, in the visible range, and the focal plane is totally adapted to astronomy with the center small array and for faster readout of the high flux target and larger array around dedicated to lower flux large field for calibration target. As I said, performance are ongoing. Our first detector development plan is shown on this slide. We've got the 46 megapixel array and it's under testing. We planned in 4 years to reach the TRL5 for the 220 megapixel gigapix. It's a co-engineering between Pixalis, the industrial firm, CNRS and CEA, and it has been funded with our national agency CNES for ARUT, for detector development and laboratory measurements. We also answered to a call for bid for dedicated Astro packaging, and we are waiting for this answer. And the development is based on this existing technology. In 4 years, we hope to have a focal plane with homemade space-like readout, electronics readout developed in labs. And 1 or 2 years after, we hope to reach the TRL5 for the astrometric, wall astrometric instrument. That means the focal plane and also the calibration unit. Next. This is this development plan and all the scheme as the experience of the assembly of a large focal plane invisible since the Saclay Lab assembled the Euclid focal plane, which was made with 46 CCD matrix in a clean room, and then participated to the test, the vacuum test, the vibration test, and all the qualification test. And also we've got a very nice picture with 600 millions of pixels, and we are ready now to go to HWO project with a 220 megapixel Pixalis CMOS to go through to rate this high accuracy, high precision astrometric instrument. So thank you very much.
Thank you very much. Are there any questions? No.
I'm wondering how you plan to address the jitter, since your requirements are the 7 microarc second, but the line of sight for the for HWO would be more like 300 microarc second.
Jérôme, do you hear the question?
If you can hear, answer in the chat.
Okay.
Or I don't know if the speaker's working.
Yeah, his call dropped, but I could hear him talk through his computer on the WebEx, so I heard him trying to answer.
Do you need a microphone or do you have one over there? Yes?
Yes, we'll see if this works.
Okay. Well, in the interest of time, we'll have,
I think relative
is,
measurement.
okay. All right, thank you very much. Thank you very much. All right, and next up is John Tesh on behalf of Dave Redding from JPL, talking about waveform sensing and control. Is he ready to go?
Hi, can everyone hear me? Let me share my PowerPoint here. See, is my audio going through?
Yes, I can hear you. Can other people hear?
Yes.
All right, we're good.
Some subset of people can hear me. Okay.
No, we need to.
You need the microphone.
Okay, great. So, yeah, as mentioned, I'm John Tesh. I'm speaking for Dave Redding, who's newly retired. And I'll be talking a little bit about different methods of waveform sensing and control for HWO worlds. Okay, so yeah, I think as everyone has probably heard by now, there are many different possibilities for waveform sensing control habitable worlds, in particular for EAC1. And so really this talk just looks at, an initial look at one potential wavefront sensing and control architecture and how they might be applied, in concert with each other to achieve, the ultra stability that we might need. And so for this, very early work, we're looking at using outputs from the EAC1 integrated modeling effort, which produces a time series of rigid body motion, among other things, and surface figure errors, which we can then plug into wavefront sensing control models to look at how they might be controlled using different sensing methods. So during the next few minutes, I'll just briefly describe, one potential wavefront sensing and control architecture and talk about, how we have at this stage integrated that into, the EAC1 integrated modeling, stop modeling process. And basically I'm going to illustrate this by walking through sort of a single end-to-end example that we've run, showing how multiple individual closed loop control simulations can be linked together to sort of demonstrate contrast right now in just a noise-free case. So I think, many people call this sort of essentially a pipe cleaning of showing that the models can talk to each other and produce sort of an expected result. Okay, so this is just a very notional high-level block diagram of what the wavefront sensing control architecture could look like, showing many possible control loops both on the telescope and the instrument side. So most notably, if you consider the left side on the telescope, one might have what we call in this study the rigid body control system using metrology, either laser metrology or edge sensors, to maintain the alignment of the segments of the telescope and the secondary mirror with respect to the optical bench, at a moderate rate. And the alignment that system maintains would be set by a combination of, a wavefront control element that looks at, that provides an absolute reference for that control system being fed either from, out of field wavefront sensing targets, or perhaps from the instrument itself. If the chronograph could offload some form of wavefront control, wavefront offsets to the telescope at a lower rate. Then on the instrument side, of course, we have sort of what's called here an electric field controller, just basically being a general stand-in box for a control algorithm that uses some kind of measurement of the electric field of the chronograph to maintain an established dark hole that's been established from electric field conjugation using high order wavefront sensing. And then tying the two together, of course, at the very beginning of the either an observing scenario or what have you would be, what's labeled here as large capture range wavefront sensing, which is meant to, basically be the, image-based wavefront sensing on the telescope side that gets the telescope alignment to within the range of what the chronograph needs to maintain chronograph performance. So in the, the context of this talk here, what we've sort of done so far is basically simulate, at a high level, not really detailed simulations at this point, but simulate at a high level, sort of these control loops shown here based on the telescope side and the instrument side, to just get a sense of how those control loops might play together. So, as I mentioned, we've been using results from EAC1 integrated modeling to investigate this. And so, here we have yet another block diagram that just shows how, how wavefront sensing and control algorithms have been incorporated into this stop modeling process for this particular case. So, this starts with, an observing scenario. At this point, as I think mentioned earlier, this is largely driven by, derived from a RST observing scenario for EAC1 at this point. That drives a thermal model and a structural model that produces nodal displacements. Those are mapped through a program called SIGFIT to produce rigid body motion displacements and surface figure. And then we can go into, then we can begin simulating what the wavefront sensing and control feedback control algorithms might do in the context of those rigid body and surface figure drifts. And so the wavefront sensing and control part of this modeling process starts with really a notional error budget, to be honest, and where we simulate, essentially an instantiation of the telescope with a particular set of both surface figure errors and initial alignments of the telescope state. We control that using wavefront sensing control measurement of the wavefront and control using the telescope degrees of freedom. That produces a set point for what we call the rigid body control system that maintains that alignment. So it's maintaining to that optimal wavefront aligned state. And then we can produce, a residual. We can play out essentially the rigid body drifts and surface figure drifts from sort of the upstream stop modeling processes in the context of that closed loop control rigid body simulation to produce closed loop time series of wavefront realizations using, the residual wavefront drift from that time series. And that can be fed into, a full instrument chronograph simulation to run an internal wavefront sensing control within the instrument and produce estimates of the contrast. So at the moment, we're reliant quite heavily on, linear optical models. So there's an example shown on the upper right, where we look at unit perturbations to telescope degrees of freedom and how they affect the wavefront, both on the primary mirror and the secondary, as well as any other optics that we have modeled so far. So, I'll just mention that there are a couple dotted lines here. So, at some point, I think, earlier, Matt East mentioned, for instance, the importance of, making sure that the metrology elements are well correlated with the surface of the optics. And so, going forward, I think that'll be just a very critical thing for us to include in the integrated modeling. We haven't quite gotten to that point yet. I think we're getting there. Detailed modeling of the thermal performance around the metrology mount points. And we also plan to look at, additional impacts from jitter, which, important to note would be pretty much completely uncontrolled at this point, at least according to this architecture. So, folding in how actuator forces from the rigid body control system affect wavefront jitter at high rates and how that affects performance in the instrument will be important as well. Okay, so let's see, just to start with this sort of notional example, again, we don't really have a formal error budget defined as of yet. And so, at this stage, we have just begun with a telescope that is, telescope realization, if you will, starting with something like 54 microns of wavefront error. So, this has been made up essentially just as a combination of random rigid body alignment and surface figure errors. In the future, that'll be drawn from an error budget, but at the moment, this is, purely based on just the notional allocation. And then, we're again not quite to the point of simulating the full alignment process using actual image-based algorithms yet. So at the moment, we just use linear sensitivities to, again, the linear optical sensitivities to assess what the control residual would be given, full access to the degrees of freedom of the telescope. And so, for this particular case, where we're starting with 54 microns of wavefront error, the wavefront error residual ends up being 35 nanometers, a combination of basically the residual surface figure error that can't be corrected with the telescope degrees of freedom. And so, you can sort of see that in the OPD on the bottom right here, the wavefront map showing, again, for this particular realization, the converged wavefront state at the conclusion of this process. So, this alignment state of the telescope optics serves as the set point now for the rigid body control system running on the telescope side. Okay, so as I just mentioned, the telescope itself would then be equipped with a control system to maintain that optimal wavefront alignment as the telescope itself goes through, roles and other maneuvers for actual science operations. So, moving from a reference star to a target star, for instance. And so, for this study at this point, we've again mainly taken a geometric approach of looking at error propagation through either metrology laser truss geometries or edge sensor geometries and how that might affect performance. So for this just initial example, we're just simulating a noise-free case where we have a full laser metrology system that can measure the 6 degrees of freedom of each optical element in the telescope and control those out. So, going forward, we'll have to investigate, perform allocations to error sources using a combination of edge sensors and metrology. But at the moment, we're just simulating the laser metrology side. So important to note here that, the rigid body control can correct for some amount of surface figure error if it can be observed. Obviously, just looking at the rigid body itself won't tell you what the surface figure is necessarily doing. But if you did have some sort of, active wavefront measurement happening, perhaps at a lower rate, you could feed that to the rigid body control system and remove that, even though it's not observable directly. Okay, so again, going back to this particular example that we're walking through, we can now take the 35 nanometer wavefront alignment target that we have from simulating the initialization of the telescope and play out rigid body drift and surface figure drift, coming out of the EAC1 integrated modeling process. And so, again, we're just at a sort of a noise-free state at the moment. So we're just assuming, essentially perfect rigid body sensing and control applied. In this case, just at 5-minute intervals, so not totally realistic quite yet. And so the plot on the right here, the red line indicates the essentially the open loop drift rigid wavefront error that we're trying to correct for, in contrast to the target wavefront, which is just constant at 35 nanometers. The gold line at the bottom, it's a little hard to tell. It looks like a straight line. That's the residual drift error that we get once the rigid body control system is closed around this target wavefront, under the impact of that open loop wavefront drift error. And so you can't really see it on the scale of this plot, but the drift error, I think perhaps the wavefront plots at the bottom are a little more illustrative. But for this initial control simulation, we're getting a residual error of about 22 picometers, mostly dominated by the residual surface figure drift. Again, not that surprising, given that it's not really observable from the telescope metrology. So again, if there was some form of periodic wavefront sensing, which we haven't included yet, that could potentially take out some of that additional surface figure drift as well. Okay, so with the telescope sort of under rigid body control, we can then, and maintaining a more or less static telescope wavefront down to the 22 picometer level, we can begin assessing what happens if we started coronagraph imaging, or particularly started digging a dark hole with electric field conjugation at that point. So if we have this notional 35 nanometer wavefront target that we are maintaining with rigid body control, we then simulate electric field conjugation against that wavefront. And again, using a very notional early coronagraph design, so 64 by 64 DMs. And again, this is sort of a noise-free, no radiometry case, just showing that we can establish a very nice dark hole based on that 35 nanometer initialized wavefront state. And then playing that again through, so now we have a dark hole established, we can do the same thing. We can now play through the residual telescope wavefront error starting from that dark hole state, and look at how does contrast evolve with time if there's no form of dark hole maintenance being performed. So if we establish a dark hole and allow the telescope to evolve with the wavefront residuals we get from the rigid body control system, this is what we get basically from that. So there's a little bit of a spike here that's I think been identified as a symmism unique to this observing scenario that we're trying to eliminate. But nonetheless, just without any kind of dark hole maintenance, you can see just this particular case. Maintaining Yep, sorry, sir.
You're good. I just wanted to, how many more slides do you have?
Oh, I can go quickly, just a few. Yeah.
Super quick. We're running late. Thanks.
Okay, no worries. Yeah, so we can move on from that point and simulate dark hole maintenance. In this case, we've looked at using Zernike wavefront sensor, updating the wavefront in both 5 and 15-minute periods. And you can see that removes a large degree of the residual wavefront drift that we have from doing just rigid body control of the telescope from those two rates. I mentioned wavefront jitter. We haven't incorporated those into the coronagraph results yet, but we just started looking at that using rigid body control actuator forces and feeding those into the structural FEM. So we've begun that process, and going forward, we'll be sort of incorporating those as well into the contrast results. And finally, just a quick plug for a test bed that we have. So we're actively investigating. We have a test bed at JPL where we're going to be investigating some of the. Obviously, this is not going to reach picometers, but it'll hopefully show some of the same disturbance rejection qualities of the telescope rigid body control system that we need, that we're modeling in these early studies. So just to wrap up here, yeah, this is very early work, of course, and we're really just getting started in showing that we can model different wavefront sensing control architectures and sort of predict ultimate level of performance within the coronagraph. So obviously, lots of work to go. Lots of additional noise sources we'll have to incorporate, and obviously adding realistic radiometry will be important as well. Okay, that's it. Thank you.
We might have time for one super quick question. Okay, one more round of applause. Thank you so much, Jonathan. Email Jonathan later. All right, next up is Dominic Benford, colleague from Astrophysics Division.
Thank you, and thank you all for staying here so very late. I know you've only got 2 people now between you and that door, and I see the last person, John Ehrenberg, is sitting over there preventing you from getting out, if that is the real John Ehrenberg this time. I've been asked to come here and speak a little bit about the Emerging Technologies Workshop, which was held at NASA's Ames Research Center back in the spring. Basically, we've heard a lot about technologies so far, so now you have to imagine these are the ones that should still look like magic, I hope. Here's a little thing about what the workshop was. I'm not going to read through this because we have very little time, just to say, I'll look at the little bottom one. August people have said progress in astronomy is largely driven by advances in technology. And so we want to advance technology far beyond what we have right now because we're going to advance astronomy that way. And we picked 4 particular areas of technology that we wanted to focus on for this workshop. And you can see them listed here: astrophotonics, AI and machine learning, advanced materials, and quantum technologies. I mean that fairly broadly. That's not everything that one could consider to be an emerging technology. There are lots of others. We've tried to keep it restricted to just a small enough number that we could manage it. And it was a workshop where we had a number of plenary style presentations, people setting the stage, but everybody who was there, the roughly 60, 65-ish people who were there for a reason, and they were all expected to do work and participate. So some of it looks like this, where they had talks, where they had panels, but a lot of it was actually more in-depth work. And I just want to summarize some of the things that were said during this in each of the areas. So astrophotonics, you probably know, is a field that uses different ways of handling light to combine it in ways that you can't do very easily in free space. It has potential for some really transformative change in the instrumentation. Some of the kinds of ideas we've heard about using things like photonic lanterns to control modes in ways that you can't very well do in free space. You can make better spectroscopy instrumentation, perhaps better coronography instrumentation using these. And I'm going to highlight one particular picture from Dan Sergo at Ames, who I think may already have left, where he talks about the possibility of an entirely on-chip coronagraph. And those are very relevant for things like HAB worlds. I'll also point out that it's broadly relevant for a lot of astrophysics applications, including the possible future of interferometry, where we can do a lot of the delay line stuff, all basically in glass. For advanced materials, I've got a nifty little video here. You can see some of the cool things that people are able to do. That sponge, those little sponges that are being compressed and relaxing, right? That's silicon carbide, or I think maybe it's aluminum oxide. That's ceramic. But if you make it the right way, it's sponge. It's sponge with the properties of ceramic. And you can see a little example of making tiny things out of glass in spongy ways. You can make materials that aren't anything like the macroscopic properties of the materials. And you've got an example in the upper right there of a diffractive Fresnel lens that's an achromatic flat lens made in 3D printing. I don't know how. Again, it's supposed to look like magic. And in the bottom, you have an example of a mirror mount where they're optimizing for mass, stiffness, thermal conductivity, and strength, and are able to beat pretty much all those parameters as an individual monolithic thing, all simultaneously. Because you can make engineered materials like this that have material properties that are just different from what you have. Now, AI and ML, especially the modern AI with generative AI, artificial intelligence is a big deal, and we wanted to keep this restricted to just the kinds of things that you could do for technology. So there's potential in transforming the way we do work, and so there's a potential to transform how we do technology development work. You can see there a little example of teaching something to improve an optic by looking at an optic, modeling how it performs in standard deterministic ways, looking at the outcome, and having a figure of merit function where you can go back and redesign things far faster than a human can. And another example is a little piece of hardware. You can see a little bracket down there at the bottom left, which was designed by an AI agent that was given requirements and spat out a bracket. And the bracket is far better than what a human would normally design. And then an even cooler thing, there's a little video from Ryan McClelland at NASA Goddard, who has developed, along with a big team, text to spacecraft. It's a little AI thing, but DaVinci, where you type in what you want, and in this case, this is an example shown, I think, in more or less real time, for somebody designing a 6U CubeSat, just by typing in requirements, just describe it. It's going to do all the work. And eventually, if you follow the video through long enough, it develops a whole bill of materials, and it goes out to places like DigiKey and Newark and says, do you have this electronic part that can do this thing? And it looks up the part and says, well, no, you can't, because you need to go to minus 40 C. So you're going to have to get a special one from Analog Devices. And it does this for you. You just ask it, and it gives you an answer. Now, quantum technology is another big thing, and we didn't want to focus too much on quantum computing, because that's only part of what quantum is for. Quantum algorithms and quantum information processing is related to that and to what we want to do for technology development. And that's on the little pictures on the far right-hand side. That's a test scene taken with a camera. The top one has a signals noise of about 100 photons. Well, I don't know about signals noise, but the signal, it's about 100 photons per pixel in that first image. And then you drop that down to about 2 photons per pixel in the second image. And then you apply a quantum-inspired algorithm that uses more phase information and polarization information, and with that same 2 photons per pixel, you get the bottom image, the bottom right, where you can pretty much see what it is. 2 photons per pixel. Kind of incredible. The little video you have running on the bottom left is one where you're using more of a quantum optics approach of separating out all of the individual modes and using mode reconstruction to do astrometry, super resolving way beyond, like orders of magnitude beyond the Rayleigh criterion. And then finally, you've got a clever little thing, light to qubit conversion. That's the middle picture. So we already do a lot of work with quantum detectors, and I mean sort of the weakly quantum detectors where, yes, there's a quantum phenomenon like something like Cooper pair splitting that is ultimately detecting the photon, but we're still treating photons like billiard balls or like a softball that Dawn might have pitched to me, and a lure photon is when she throws it at me slightly harder. But we want to have truly fully quantum detectors, ones where you don't sample the photon, where you store the information contained in the wave function of the electromagnetic energy that is the photon, and you process that. You can do new things with that kind of approach. Now, I said what we were talking about in the various presentations, but the real work was actually done in breakout sessions where people got together, and this being a very high-tech workshop, we did everything on whiteboards. Because that is actually a really efficient way for multiple people to contribute. And so we had all the subject matter experts for a given technology in one room and discussed all sorts of aspects about what can be done to push this forward and make these emerging technologies closer to reality. And then we started mixing pairwise all of these groups together so that we could start looking for the commonalities, the cross-pollination between these. And this is really where a lot of the focus was. How can you use these things in combination to do even more? And some of the results are really spectacular. The deliverables ultimately from this, yes, there's going to be a write-up that describes all of the things that happened after the multiple days of very, very smart people working in rooms together. I was one of the people watching the smart people working, not one of the smart people. And so we're going to have a write-up about all of this, but we have some things that can come out of this directly. And I'll just present those very quickly. This is sort of fulfilling the miracles that we're going to have for something like the Habitable Worlds Observatory or for telescopes beyond that. Obviously, things like a photonic coronagraph and or a photonic, some kind of multi-object photonic spectrometer are things that are close enough to within reach that we can look towards getting those into tiny little bits of glass. Single photon detection with the weakly quantum devices is a real thing. We already are doing that. Advanced materials are something which they're already demonstrating we can probably push towards. And some of the advanced materials include things like impact mitigation for micrometeorites, because you can make carefully designed little foamy structures that can stop amazing amounts of energy in very short spaces. And also ultra stability. And I've got a little example of a press release for an unrelated bit of NASA work. Alvar, this is one of these newly engineered metals. It has a coefficient of thermal expansion that is designed to be basically the same as aluminum, except the sign is the other way. So that if you build this in concert with these two materials together, you can make things that have, with varieties of different metals, that always have near zero CTE for a reasonable temperature range. We want to enable better designs using AI to enhance what humans can do. And so you've got, again, there's Ryan McClellan with one of his brackets that a computer invented for him. And because of the cross-pollination, what you can envision is combine all these things together and have an AI designed diffraction controlling an optic in photonic space made with advanced materials and all of this used together simultaneously. And this is within reach with the stuff that we pretty much have in the laboratories right now. And so more broadly, what we are trying to do is to set up connections between the experts that we have there and the Hab Worlds project so that we can make use of these emerging technologies where they are mature enough and where they are appropriate. We've already been incorporating some of the more innovation-oriented thinking into the solicitations. We're piloting an internal solicitation where you don't have to know how to do it. You have to know what you're trying to do. And that's a bit of a different way from the usual technology development where we, frankly, tend to focus a bit on, do you know how to do it? And we're trying to connect more across NASA and across other agencies because there are lots of other people who have similar technologies that they might be working on for completely different purposes that we want to partner with more. So recently you got a little paper there on quantum sensing that NASA is doing. We're trying to advertise this in part because we want all the other agencies, both in the US and abroad, that are working on quantum technologies to work with us on these things. You've got an example of a DARPA quantum super resolution picture down there. And then finally, we're trying to bring more people sort of into the NASA fold. So you've got some little presentations that we have, little screenshots of people who we invite in to come and talk about the great technologies that they're doing for other purposes elsewhere that we can learn from. That was the point of having an emerging technologies workshop. And we hope that some of these things can eventually find their way into Hab Worlds and future missions. And if you have more interest in this, this is just our beginning. Please come and talk to me. Thank you.
Any questions for him?
Yes, you do. Thank you. We do have an online question.
Great, go ahead.
Oh, I should have given credit to Mario Perez and Nick Sealer, who were really the ones who were working on this, but they couldn't be here to talk about it.
Online, Michael Best says, we're exploring a hybrid path to wide spectrum interferometric imaging using AI-assisted reconstruction methods. In your view, is there still room in the HWO roadmap for emerging alternative collection architectures, particularly from smaller or cross-disciplinary teams aiming to complement the mission?
That's a long question. It almost sounds like you could have asked ChatGPT, what's the best question to ask at the end of this talk? And maybe we'll come up with that. So I'll address part of that. Is there still room in the Hab Worlds project to incorporate kinds of emerging technologies like we discussed here? Possibly. I don't think I would rule any of that out. Julie's going to stare at me and be like, shh, shh, shh. Because we do have a little bit of time to develop these, and many of them are actually fairly mature, but they haven't been used for space purposes yet. But that's, TRL3 for a lot of these, so that's not inconceivable. They just have to come to fruition really quickly. Completely different architectures, that's a lift that is, well, first of all, other people in this room will determine this, but that's a lift that would take a bit more rationale behind it. If you wanted to have something like, let's say, a completely planar surface populated with little receivers, all astrophotonically combined, yeah, the physics allows you to do that, but that really is pretty magic. I hope that answers the question.
All right, one more. Quick.
I was curious to know where we can, like, is there any online information about the new solicitations? Because we've been proposing photonics for 2 years for HWO, so I'm curious about that.
Sure, I will say that you can already propose things, generally speaking, to the APRA, Astrophysics Research and Analysis call. There isn't one in ROSES 25, sorry about that, you know how things are right now. But there should be another one in ROSES 26 that'll be coming out in February. And I would like to say that the purpose of this isn't to change the kinds of technologies we're soliciting for, although that may be a possible outcome, but actually to change the way we're evaluating these, to look at putting more emphasis on whether the idea is compelling and a little less emphasis on whether you have figured out everything about how you're going to make it happen. I mean, you can't make magic happen if you're spending all your time looking at the ways that it will not work.
All right, thank you very much, Dominic. Last but not least is John Ehrenberg from Northrop Grumman.
Assuming right means go.
Okay, so for those of you who are here on the first day, I'm in what Bruce McIntosh says is the coveted ultimate or last position. So we're going to talk a little bit about concept maturity levels. John Ziemer has already given us an elegant introduction to that concept of understanding how we're going to use something. Originally, this was going to be entirely directed at servicing, and as you'll see, that the subject is much broader of how we properly integrate something as revolutionary as servicing into our potential observatory design. So let's begin. I've spent my career, as I told you when I was Charlie Atkinson earlier today, largely working on flagship missions. These are two large flagship missions that are solidly of their generation, and we're going to talk about generational change. It is worth noting that what is now called Chandra started out life as AXAF and was supposed to be a serviceable mission a la Hubble with multiple generations of instruments and visits by astronauts. And when there was a 70% budget cut, the future instruments and the servicing was taken out, the orbit was changed. And that's how it became an unserviceable mission. But servicing and the opportunities that it provides for advancement in science is hardly new. It's just been hard to implement. To frame our talk, I want to introduce some terms. So just like we're in this room that's got a vast number of generations, and we're talking about generational change in the way we imagine future flagship missions, I want to introduce you to my version of the 3 space ages. The first space age was very early. So it was from prehistory to the Apollo 1 fire. And it was made of whatever was laying around, put it together, just make it work. So you can go visit the amazingly brave and very limited spacesuits that the original astronauts flew in, Mercury capsules. All very daring. At the time of the Apollo 1 fire, a deadly serious accident became the era, what I call middle space, mesospace, space 2.0. Failure is not an option. And that's largely been the mantra for the career of most of the people in this room. There's a division indicated by the activity in the red framed box. This was what Joe Anderson alluded to, our MEV-1 mission. This was a robotic servicing mission of an unprepared spacecraft. So I will divide the middle space age into early and late middle space age. And we're standing on the cusp of an engineering revolution. That's John Wilkinson. He was probably the pointy end of the spear on the Industrial Revolution. We can have a debate with any history professors, but that's why he's there, to indicate that we're on the cusp of this new revolution that I call Space 3.0 or New Space. Servicing, in my mind, is the harbinger of that revolution. But to take full advantage of it, we have to try to understand everything that's going on, because in fact, the business of designing these types of observatories is about to undergo serious change. And we've heard a number of questions here that, depending on what generation you're thinking about, like when do we have to freeze the technology? Those questions almost don't apply in this new framework. And so there's a lot of decisions about whether we're going to build HWO in the old style or in the new style or in some hybrid style. I'm sure I could make some architectural reference to cathedrals, but I will skip it. So characterizing what I will call the new space milieu, it is certainly characterized by vastly more players. This is not the two nations, great superpower nation state actors. There are many, many more nations that are spacefaring, both in terms of launchers and payloads, operations, and certainly many, many private concerns, large, small, new, well-established. There's now things like commercial launch services, space servicing, and robotics. And I'll emphasize again that our current business is entirely commercial. That is absolutely a sea state in operations. Robotics, advanced machining, advanced manufacturing, you've heard lots and lots and lots of examples, and so on down the line. So I would say that right now, with the proof that we're in the late middle space age, we're at about concept maturity level 2. That is, there's some feasibility, some concept of executing this anywhere, anytime. Now we've got to figure out what we want to do and start trading it and figuring out what's the best deal for the program. This brings us to the big question. How can we imagine Habitable Worlds Observatory as a neospace mission? How can we imagine it as a fully Space 3.0 architecture, program, and cultural approach to solving the problem? This is very different. There's very different questions, as I've alluded to already, and I'll illustrate in the paper. I don't want to go through all of them right now. So we're in effect designing this concept. So I've listed what I call the 8 steps in the design process. Now the last 3 really refer to hardware, but we're going to concentrate on the first couple. We want to know and understand what the customer wants. In this case, the customer is HWO. Okay? We want to ask the design question in a way that we can answer it and respond. So this includes, how do we measure it? We want to do the best thing for HWO. Is that in terms of science performance today, potential science performance in the future, cost, schedule? It's unclear, right? So we need to lay all these things out and push them around the table, and as a community decide, what do we like, what do we not like? To answer those questions, we need to be unencumbered by limits and think of all of the design solutions, because when we go through and try to pick the best option under what's best for the mission, most of them will fall out, quite frankly. And we want to understand how they work together and benefit, and in fact, how they might cause failures and otherwise be unpopular to come to the best answer. And we'll go through that a few times. And this is generally what we're going to do. Right now, because we've just started, we're really concentrating on the first 2 steps. So let's take a step and say, what are we trying to fix? What makes design in the middle space age so hard? So first of all the missions are self-contained. Everything's got to show up at one time, go in one fairing, be there when the launch director hits the go button, and that means everything's got to fit in the fairing. You've got to face the tyrant, the tyranny of the fairing, mass volume limitations. Schedule is driven by the last element, which means the cost is driven by the last is tail end Charlie. Cultural pressure to not fail. This can drive, depending on your reviewers, unplanned extreme actions, etc. Got to get exquisite performance, current communications, technology, and rates present limitations, driving complications into the science instruments. And if you go read the cost literature, really exciting stuff, you will find out that by and large, the most expensive thing on the observatory, not surprisingly, is the instruments, right? So the very fact that we're throttling them and making them more complicated with complicated modes drives up cost. If Michael Werner were here and telling you about how they achieved wonderful things on Spitzer, he would say simple, simple, simple. Fewer modes, the better. So we can't do that when we want to get all our data down this little thin pipe, okay? And then of course, the lesson of newness, which is our JWST lesson learned about trying to develop and understand how the system works at the same time, presents intrinsic and fundamental risks. And we're developing a flagship, which is fundamentally fraught because it's got a huge community, it's got huge visibility. Once promises are made to a broad community, you can't retreat, and it's fundamentally fraught, and that's me on the way to CDR getting shot at. Okay? Not really. Not really. Okay? I'm sure this is being recorded. That was a joke, okay? And yes, this was taken by a US government employee because he was in the process of bombing the battleship there. Okay. There's also parametric models that basically don't apply. So what I did is I took Phil's cost model and I put in a few parameters for what might be the limiting wavelength and showing a cost multiplier relative to JWST. So however you define it, people might say, oh, well, that stability is like trying to build a 100 picometer diffraction limited telescope, which in some respects it is, but probably not appropriate. And some people might say, well, don't even start HWO, it's going to be 12 times more expensive than Webb. No matter what we do, we're going to have to think about costs and more appropriately face the problem of perceived cost. So if we can avoid cost by exploiting Space 3.0 to reduce scope, defer things, decomplicate them, shorten them, we will gain significant benefit. So what is of value to HWO? There on the left, I tried to make a quick list of things off the top of my head. Cost, schedule, scientific performance, flexibility, etc. Ways to manage it and measure it are on the right. Those are going to be figures of merit because those will drive the design and the selection. I imagine those, as the discussion goes on, will be topics of a hot debate. So here, and we're going to go through this quickly, this is essentially the central result of the paper. If you look on the left column, this is all of the perceived issues and design challenges in making a mesospace system. And each of the columns with an X in it says, yes, in my quick estimation and analysis, there's something in the Neospace catalog in Canon that will help us reduce the cost, reduce the risk, reduce the problem. Okay, so we're going to step through this fairly quickly because I want to end on time and allow for maybe a question or two because I'm standing between me and my post-conference cocktail. I have no intention of being late. So when we talk about servicing writ large, it does allow us to conduct post-launch operations. It does allow us to consider the addition of new science instruments, new capabilities. Maybe the mid-X's of the future will not only be small satellites, but they might be new capabilities for habitable world and its sister future great observatories. Maybe. Larger apertures enable more science. We can replace hardware. We've talked a lot about that. Is that really the best value? We're going to talk about the large launchers that would allow us to put a bigger gas tank on, additional redundancy. Is that a better economic deal than going up and paying for a service mission? It will certainly depend on the cost of the service mission. But that's a question Space 3.0 allows you to add. Question of possible cost and schedule reduction by not waiting for tail end Charlie. You set a date when the train is leaving the station, and if your instrument isn't there on that date, stay on the ground. Right? This is a tremendous management tool, assuming that the minimum capability is available by go date. But certainly if you have an event, like having a minimum complement ready, and you've got 4 or 5 events that can happen and you only need 3, that's a good way to ensure success. Advanced communication. Optical communication is being driven by many other players elsewhere in the market. It will be available. It's almost commercially available now. There will be large infrastructures, ground stations, and even in the probe call, we were allowed to consider commercial ground stations. So even now, NASA's thinking more broadly. If you can design a simple instrument, even one with a big focal plane, and the design paradigm is just send it all to the ground, where some of the amazing AI and advanced computing can work on it, and you're not flying that, so you're not stuck with a 386 trying to do AI and machine learning in space, because that's about where we'll be in 2045 under the current paradigm, you can do amazing things. Furthermore, you can also imagine that each instrument, if it has extraordinary comm needs, comes with its own optical link, because they're essentially completely independent. But also, perhaps these modern links allow for cross-link between observatories, giving significant TDAM advantage, which is likely to be a science thing here in the future. AI/ML is now even being planned for ground operations of constellations. So it can significantly increase the operation of an observatory ground team. It also has potential advantages for trending in a way that we have never done during INT, relaxing some of the requirements later in INT and allowing us to move the hardware smoothly through the process. Large launchers certainly reduce mass and volumetric limits. It allows us to consider bigger things differently, exquisitely optimized, and it allows us to trade the requirement or the desirement for long life with redundancy versus servicing for the best economic value. Needless to say, as we push towards picometer stability over a wide variety of opportunities, we're going to push modeling capabilities to its extreme. There have been lots of talk about post-processing with these advanced computing tools. It will certainly, no doubt, be of great help to the integrated modelers of the future with models that have 10 million degrees of freedom, and they've got to find the right variables. One of the absolute most important parts of new space is all the other players. Under the old regime, under the engineering culture, the mission development culture that we all grew up in, and I mean this pan-generational, is all teed off of the nation-state model. There was no commercial market. You couldn't just go down the street and buy something. You'd go rent a satellite communication ground station. You can do that now. There will be people doing manufacturing in orbit, demanding high bandwidth communications. We will be able to use that. Servicing. Already made the argument 3 times that it's commercial. That's going to continue to develop because those customers are going to want to retrieve their factory in the sky that's making fiber optics or pharmaceuticals or sunglasses or flip-flops or whatever they're going to make in orbit, right? And so our design paradigm is to follow that roadmap and see what we can adapt. That's fundamentally different than developing that technology ourselves. I stepped on my own conclusion there. Come on, come on. There we go. So I saved that last column. So if there was any X in any of the horizontal rows, any of the challenges presented by imagining ourselves as a mesospace program, even just one, I said yes or green. And as you can see, that whole column is green. So there's something for everybody in terms of their challenges in design, in considering the benefits, the opportunities that new space affords us. As we consider that, let's remember that if we want to bake that into the architecture, now is the time to think about it and get it in, because unfortunately, it will be much harder to get in it later. It does have the opportunity to help in a profound way. We have to make sober cost exchange and benefit analysis. So just because we can go up and change a resistor in a board or the actuators behind a mirror, we may or may not want to do that because it may make too big an opportunity cost for the mission. but there's a lot of opportunity in this space. And with that, I will say, hopefully end on that hopeful note so that this end of the flight was a smooth landing, not like we're all going to enjoy flying out of here in the rainstorm. And say one more thing. The last chairman addressed this as dessert after lunch, so I guess that means I get to be the cherry on the sundae. So 3 bucket list items in one day. This conference is awesome. I want to thank you for your kind attention, sticking with us to the bitter end, and I look forward to any questions.
Any questions for John online or in the room?
Hi, John, it's Todd. We spoke over it, but I guess one of the questions that I have, and this might be a question that is really in tangent with everyone else. How do we balance the ideas of thinking about servicing too early versus too late in the conceptual models?
So I think we look at all the options, and again, there's going to have to be a very serious discussion about what kinds of benefits does the program want to yield, to get out of this deal, and that will help sort it. So again, it's following this process of identifying what's important and evaluating the options against that's important, against those figures of merit. And at some point, like any program, there'll be finite resources and there'll be a list of things that we incorporate and things that we don't.
Sorry, one quick question. So when you think about Space 3.0 and you think about our process with the decadal, how do you see that working together?
That's a good one. All right, I'm just going to answer standing here since everybody's expecting an answer. This is as much a cultural as an engineering change. And so we really have to view habitable worlds as a facility, right? So it's going to provide the capability to accept future instruments or future capabilities, or it's going to be the last of the mesospace projects where everything goes at once. And I think it's just a matter of the resources and the time and how fast people want things and how deeply we want to think about it. So it does profoundly change the questions that we ask ourselves. Like I think somebody asked the question, well, when do we have to decide on which technology? No, you have a bunch of them. You take the best one that's ready, that goes into the instrument. The others can develop, but there's an opportunity later to come back in, either as part of the mission if it's needed, it has to be costed, of course, or then it can come back later as an additional mission or an enhancement. And so I think it's going to force us to think fundamentally differently. And I did have an answer, by the way, for the chair's question about what about a future detector that needs a cooler, right? We don't want to disturb the observatory, but because we can service it, the doer now becomes much more attractive because we can refill it. So I think it does open up opportunities to think about design in a fundamentally different way, right? And we get to ask what we want and have more ways to solve the problem.
So I've been told we're being asked by the Bloomberg Center to evacuate. So
I've been thrown out of better places.
But we also want to thank you, John. Thank you, John, and a big round of applause for Don and all of the speakers in the back and in his testimony. And go have that cocktail, John. Thanks, everybody. Thanks for coming here. And safe travels home to everyone. And thank you so much for coming and making this such a memorable event. Appreciate it.
I'll just put this up here.